Hello there and welcome to Science for Sleep, where curiosity gets cozy and exploration drifts softly into imagination, where each question invites calm and wonder rather than urgency, and where the vastness of the universe feels just close enough to ponder while your mind relaxes. Tonight, I want to take you on a gentle journey, a voyage not through the ticking of a clock or the folding of days, but through the immeasurable stretches of space, to consider one of humanity's most profound and quietly unsettling questions. What is the absolute limit of human space travel? How far could we ever hope to go, not just in miles or kilometers, but in scope and possibility, in years and lifetimes, in the very endurance of our species? As we settle in, perhaps with a warm cup nearby and a quiet space around us, I wonder where in the world you're joining from, and if the thought of our fragile blue planet shrinking into a distant dot brings a sense of awe or gentle anxiety, or maybe even a quiet thrill. Where are you listening from tonight? What thoughts are swirling in the spaces just beyond your awareness as you tune in, seeking the slow rhythm of reflection? It's curious, isn't it, that as humans we have always been dreamers of distant horizons, our imaginations carrying us beyond the constraints of our immediate environment, yet so firmly tethered to our bodies, our limits, and the fragile envelope of air and gravity that keeps us alive. If this exploration, however tentative and soft, brings you a measure of calm or curiosity, perhaps you might like the video, or subscribe to this quiet corner of contemplation so that these gentle voyages can continue, carrying anyone else who might need a pause from the noise of their day into the slowly unfolding spaces of thought and universe. And so, with your presence here, in this very moment, and with the knowledge that even as I speak we're all moving through space, orbiting a sun, sliding imperceptibly around a galaxy, I invite you to let your thoughts drift outward with mine, as we begin to consider what it truly means to travel beyond the bounds of our world. Human space travel has been a story of small beginnings, rockets that roar into the sky, shaking the ground beneath us, mark the start of something much more profound than the simple act of leaving Earth. They are our first whispers into the void, the beginning of a conversation with the universe, a conversation that is measured not only in distance but in imagination, in persistence, in the patient folding of technology into dreams. When the first humans climbed into those slender capsules, strapped against engines and fire, they were propelled not only by fuel but by centuries of curiosity and the quiet hope that someone, somewhere, would look back at Earth and feel the tender vulnerability of our place in the cosmos. Each mission, from the earliest suborbital flights to the Apollo journeys to the Moon, carries both an immediate physical purpose and a larger, almost philosophical one, a demonstration of what it means to move beyond the familiar. And yet, the more we venture outward, the more we are confronted with the fundamental questions that underpin our existence. How far can we actually go? How do we sustain life over the long stretches of time and distance that separate us from other stars? How do we balance our ambitions with the limits of matter, energy, and the human body itself? It is a question that unfolds on many levels, simultaneously technical, biological, and deeply human, and it is precisely this layering that makes it so compelling to consider in a slow, contemplative way. The journey of human exploration is shaped not only by the engineering of propulsion and spacecraft, but also by the limitations of our own biology. Our bodies, evolved for life on a planet with a specific gravity, atmospheric composition, and radiation shielding, are remarkable in their resilience but fragile in ways that become increasingly apparent the farther we move from the Earth's protective environment. Space is a place that demands adaptation, from microgravity's effects on muscle and bone to exposure to cosmic radiation that our planet's magnetosphere would normally intercept. Even something as simple as the rhythm of sleep becomes precarious when natural day and night cycles are absent. And so, as we imagine the absolute limit of human travel, it is impossible to separate the physics of distance and velocity from the physiology of life, from the subtleties of psychological endurance, from the faint pervasive need to breathe, to sleep, to sustain ourselves across vast stretches of emptiness. These constraints shape not only the feasibility of missions, but the very imagination of what is possible, forcing us to reckon with both the known and the hypothetical in equal measure. Yet the cosmos, as vast as it is, has always seemed just within reach of our curiosity. We measure distances in light years, pass time in centuries, and speak of stars as neighbours in a neighbourhood too immense to fully comprehend. And in that enormity lies both humility and inspiration. The speed of light, for instance, is an unyielding law of physics, a ceiling that limits the pace at which we can traverse interstellar space. No matter how sophisticated our propulsion system become, no matter how far we refine our understanding of matter and energy, there is a fundamental boundary that shapes what can be achieved. It is not only the distance, but the time it takes to cross it, and the effects of prolonged travel on both the spacecraft and the human occupants that define the edge of possibility. In considering this, it becomes clear that human space travel is not merely a technological challenge, but a contemplation of scale, endurance, and the meaning of exploration itself. And as we drift into this reflection, it is worth noticing the quiet paradox at the heart of space travel. We launch into the void to discover the universe, yet every journey also reflects back on us, illuminating the limits of our own bodies, the ingenuity of our minds, and the subtle, delicate networks of life that sustain us. The vacuum beyond Earth is both a mirror and a frontier, demanding both respect and imagination. The questions we ask about propulsion, energy, radiation, and sustainability are intertwined with questions about the human spirit, the persistence of curiosity, and the ways in which we define what it means to reach beyond ourselves. Perhaps it is this duality, the technical and the personal, the measurable and the experiential, that makes contemplating the absolute limit of human space travel such a gentle, absorbing meditation. Even as we consider the theoretical boundaries, it is fascinating to reflect on what has already been achieved. Human ingenuity has placed astronauts into orbit, on the moon, and sent probes to the outer planets and beyond, each mission pushing forward the frontiers of knowledge and testing the resilience of life and machines. These small steps, often measured in increments that seem almost insignificant compared to the expanses we dream of crossing, are nonetheless profound. Each success offers insight into what might be possible, revealing both obstacles and potential pathways, and as we imagine what lies ahead, it is comforting to consider that these boundaries are not static. They shift with each technological advance, each discovery, each experiment that teaches us how to sustain life, protect the human body, and traverse the distances that would otherwise seem insurmountable. As we begin to trace the contours of this vast question, we might consider not only speed, propulsion, and life support, but also the ways in which time itself becomes a companion to distance. Relativity teaches us that moving at high velocities alters the experience of time, that the passage of seconds for a traveller may differ subtly from those who remain behind. The psychological aspects of long-duration travel become intertwined with physics, shaping perception, endurance, and the very experience of life on a journey that may extend over decades or generations. Here, human space travel is not merely about technology or ambition. It is about consciousness, perception, and adaptation, and the way our experience of reality bends along with the constraints of the cosmos. And so, with your presence here in this quiet, shared moment, we begin not with the full technicalities or formulas, but with the gentle awareness of both possibility and limitation. We consider the dream of leaving Earth not as a single point in time or space, but as a continuum, an unfolding story of human ingenuity, imagination, and resilience. And where might we go if we could endure the distances, the radiation, the solitude, and the years it would take to reach distant stars? How would our bodies, minds, and spirits adapt to journeys that stretch beyond familiar cycles of day and night, life and rest. And how do these contemplations, in their slow unfolding, reflect back on us here, in the soft glow of screens or candlelight, reminding us that even while we remain on our small planet, our thoughts and dreams can drift among the stars gently, deliberately, and without hurry. Human space travel is a tapestry woven from physics, biology, psychology, and imagination. It is a pursuit of knowledge and survival, a meditation on endurance and limits. Even as we dream of voyages beyond the solar system, even as we contemplate concepts like multi-generational ships, hibernation, or speculative propulsion, the act of imagining these journeys brings insight into our own existence. We measure not only distance but fragility, resilience, and creativity. Every calculation, every design, every thought experiment about what lies at the ultimate edge of human reach becomes a meditation on who we are, how we endure, and how far we can hope to travel both physically and intellectually. Let the journey start quietly, with the soft pulse of curiosity, the hum of imagination, and the gentle unfolding of thought that will carry us outward, ever outward, into the questions that define the absolute limit of human space travel. Even the smallest steps can feel monumental when the stage is infinite, and humanity's first ventures into space were exactly that. Tiny steps on a stage so vast that perspective alone reshapes how we think about existence. It begins with the understanding that Earth, this familiar sphere beneath our feet, is just one among countless celestial bodies in a universe so expansive that even the speed of light can barely bridge its gaps in a human lifetime. When Yuri Gagarin first orbited the planet in 1961, his journey lasted a mere 90 minutes, yet for those who watched, and for humanity as a whole, it was a profound moment. A single human, strapped into a metal capsule, rocketing above the clouds, tracing a circle around the blue planet, our home, from a vantage point we'd never experienced before. That orbit, brief and unassuming to some, represents an extraordinary combination of physics, engineering, courage, and the quiet persistence of curiosity. The steps may have been small in distance, but the implications were immense. At the heart of these early missions was the recognition of limits and the constant negotiation between ambition and reality. Rockets needed fuel, the human body needed air and protection, and every calculation was precise because error, even slight, could mean catastrophe. The bravery required was not just physical, but existential. When Gagarin looked down on Earth, he saw a horizon unlike any we had imagined, and simultaneously he felt the vulnerability of life beyond the thin envelope of atmosphere that cradles all terrestrial creatures. The tiny step was a reminder that while space may be accessible, it is unforgiving, indifferent to our presence, and enormous in ways that the mind can barely comprehend. For those first astronauts, every heartbeat, every breath, every vibration of the spacecraft was a negotiation with reality itself. Yet, the view they returned with forever altered humanity's sense of scale and possibility, showing us that the borders we once imagined as fixed are far more flexible than previously thought. Beyond the individual missions, the significance of these early journeys lay in perspective. From orbit, continents shrink, oceans merge into vast bands of blue, and weather systems swirl in patterns only partially understood from the ground. The borders, nations, and conflicts that dominate daily life dissolve into subtle gradients and patterns. Humanity, in those brief orbits, could be seen as a single organism inhabiting a fragile sphere, floating in an otherwise dark and indifferent expanse. This perception, gained in just a few minutes of orbital flight, reveals the duality of human space travel, technically minor and physically constrained, yet psychologically and culturally transformative. The tiny step of a single orbiting capsule opened the door to a broader consciousness, a recognition of scale and context that cannot be gained from any terrestrial perspective. As the early missions progressed, they tested not only technology, but the limits of human endurance and adaptation. Weightlessness, which may sound whimsical or even liberating, presented profound challenges. Muscles weaken, bones lose density, and fluid distribution shifts in the body, affecting vision, balance, and even cognition. The human body is finely tuned to a gravitational environment, and removing that gravity, even temporarily, alters every system. Early astronauts had to adapt quickly to these changes, relying on extensive training and strict protocols to maintain health and functionality. Even the smallest movements had to be calculated, every action in orbit requiring consideration of inertia and momentum. The environment that is so familiar and supportive on Earth becomes alien and demanding beyond our atmosphere. In this way, the first steps of human space travel are simultaneously a demonstration of capability and a gentle introduction to the constraints that define what is possible. Each incremental achievement, whether launching into orbit or performing a simple spacewalk, carried lessons far beyond its immediate success. Spacecraft design evolved rapidly in response to the realities of human physiology and orbital mechanics. Systems for air circulation, temperature control, and waste management became more sophisticated, ensuring not just survival, but the capacity for extended activity. Even the psychological demands were considered. Isolation, confinement, and sensory monotony create cognitive and emotional stressors that can become as dangerous as mechanical failures. The tiny step in this sense was multi-dimensional, involving not only propulsion and engineering but also life support, medical research, and the study of how humans perceive and interact with a completely new environment. Each step forward required careful attention to countless variables, revealing both the fragility and resilience of life in space. It is worth pausing to consider the human perception of scale in these early ventures. A low Earth orbit may be only a few hundred kilometers above the surface, yet that distance is beyond any experience available on the planet itself. From this vantage point, the Earth curves visibly against the blackness of space, the thin blue line of atmosphere separating life from void. The scale of the cosmos begins to intrude even in the first stages of travel. Every orbit reinforces the awareness that our home planet, as vast as it seems from the ground, is small and delicate in a broader context. For those who have observed the planet from orbit, the perspective is often described as transformative, a quiet, ongoing realization that the world we inhabit is finite, yet capable of sustaining life in intricate balance. These moments, brief though they may be, become a lens through which all subsequent ambitions for space travel are measured. As exploration extended beyond single orbits, missions to the Moon demonstrated the psychological and technical challenges of leaving the Earth's gravitational influence entirely. The Apollo missions required not only powerful propulsion systems to escape Earth, but also meticulous planning to sustain life across days of travel, to navigate with extreme precision, and to ensure safe return. The distances, though small on a cosmic scale, are orders of magnitude greater than orbital flights, and the margin for error diminishes sharply. Every maneuver, every trajectory adjustment, carries consequences for both success and survival. The tiny step on a vast stage becomes more pronounced, and the realization of human limitation becomes intertwined with our capacity for ingenuity. The Moon missions exemplify this duality, highlighting the interplay between constraint and aspiration, and showing that even within the immediate solar system, travel requires careful orchestration of technology, biology, and human decision-making. In reflecting on these first steps, it becomes clear that perspective is as important as propulsion. A single orbit, a moon landing, or even the journeys of robotic probes shape our understanding not only of distance, but of time, endurance, and scale. The progression from low Earth orbit to lunar exploration is incremental in physical distance, but exponential in knowledge gained. Each experiment, observation and challenge encountered informs the limits of human activity and the preparation necessary for more ambitious endeavours. The tiny steps are far more than symbolic. They're essential milestones that define the parameters of what can be achieved, offering insight into both practical constraints and the broader philosophical considerations of venturing into the cosmos. Another aspect of these early ventures is the evolution of collaboration and global participation. While the space race initially emphasized competition between nations, the shared knowledge and experience gained laid the groundwork for international cooperation. Missions became collaborative efforts in technology, observation, and research, illustrating that the limits of human space travel are not solely determined by individual capability, but by collective ingenuity. The tiny steps are therefore not just physical or technical, they are social, intellectual, and cultural, reinforcing the idea that reaching beyond Earth is a multi-dimensional challenge that requires integration across disciplines, countries, and perspectives. Even as we consider these early moments, it is easy to overlook the subtle ways in which our first ventures into space inform current ambitions. Low Earth orbit serves as a testing ground, a laboratory for prolonged human presence beyond the immediate shelter of the atmosphere. Experiments in orbital habitats reveal the impact of microgravity, isolation, and extended duration on both humans and machinery. Every rotation around the planet accumulates data critical for understanding the possibilities and constraints of interplanetary travel. The tiny steps of orbiting the Earth and stepping on the Moon are, in essence, rehearsals for the more distant journeys we may one day attempt. They allow us to evaluate not only physical systems, but psychological endurance, problem-solving under stress, and the rhythms of life in environments entirely unlike the one in which humans evolved. The human imagination is closely tied to these achievements. Even brief glimpses of Earth from orbit inspire new ways of thinking about the planet, the cosmos, and our place within it. They expand our sense of possibility while grounding us in the realities of survival, propulsion, and navigation. It is this interplay between wonder and constraint, aspiration and practicality, that defines the early stages of human space travel. We learn to measure distances, not only in kilometers, but in energy, time, and risk. We learn to consider the limitations of human physiology alongside the potential of technological innovation. And through these lessons, the boundaries of what is possible become clearer, shaping the ambitions that will carry us further into the universe. And so, these tiny steps on a vast stage carry implications far beyond their immediate achievements. They remind us that space is expansive, indifferent, and demanding, and that every advance must account for the limits of human capability and the constraints imposed by physics. They show us that exploration is both an external journey and an internal one, requiring adaptation, ingenuity, and the careful calibration of expectation. These first steps serve as the foundation for imagining not just the next mission, but the ultimate boundaries of human reach, offering lessons in persistence, perspective, and the quiet, enduring rhythm of curiosity that drives us outward. Even as the first humans returned from orbit and lunar exploration, the questions remained, extending far beyond the achievements themselves. How long could humans survive in transit to more distant destinations? What would be necessary to support life for months or years in space, without the immediate reassurance of Earth below? How would the passage of time, the accumulation of isolation, and the slow stresses of microgravity shape the experience of travel? These questions flow naturally from the initial steps, each one expanding our understanding of the challenges that lie ahead, and reinforcing the sense that what is achievable is defined as much by preparation, endurance, and imagination as by propulsion or distance. And so, from orbiting Earth to stepping on the Moon, humanity has begun to define itself not only by the limits of what we can reach physically, but by the patience, adaptation, and ingenuity that allow us to exist beyond our native environment. Every small movement into the void, every test of systems, every observation from space carries lessons that inform how far we might one day go, how we might survive, and how we might perceive the vast stretches that lie ahead. Even as humanity took its first orbital steps, it became clear that those small orbits were only the beginning. To truly explore beyond the immediate neighbourhood of Earth, we needed a way to move faster, farther, and more efficiently. And so rockets became the tangible expression of our dreams, the engines that convert human imagination into motion through space. They are more than mere machines. They are the physical manifestation of our desire to touch the stars, a bridge between aspiration and reality. Each launch, with its plume of fire and clouds of smoke, is a rehearsal in the delicate dance between physics and ambition, a reminder that to go further, we must reconcile the limits of matter and energy with the boundless reach of human curiosity. The dream of reaching the stars begins in the controlled chaos of liftoff, and every successive improvement in propulsion technology reflects a balance between careful calculation and hopeful daring. The first rockets that carried humans into space were remarkably simple in concept, yet extraordinarily complex in execution. They relied on the basic principle of action and reaction, expelling mass in one direction to generate motion in the opposite. On paper, this seems elegant, straightforward, and even charmingly simple. In practice, it demands precise engineering, perfect timing, and meticulous attention to countless variables: temperature, pressure, material strength, fuel composition, and structural integrity all converge to determine whether a rocket soars into orbit or fails catastrophically. Early engineers and scientists understood that every kilogram of mass, every milliliter of fuel, and every change in trajectory could tip the balance between success and failure. Yet they pursued these ventures with persistent optimism, driven by visions of distant horizons and the possibility of human presence beyond the planet that nurtured us. It is fascinating to consider that these rockets, which carry humans into orbit, are simultaneously technological marvels and symbols of our collective hope. The engines that roar to life on the launch pad are fueled not just by chemical propellants, but by decades of research, countless experiments, and the quiet conviction that it is worth risking everything to extend our reach. The immense pressures, the intense acceleration, and the extreme temperatures are all part of a carefully choreographed process, designed to overcome the constraints of Earth's gravity and atmosphere. Each ascent is a negotiation with natural forces, a careful translation of human ambition into motion, and a test of our capacity to coexist with, rather than dominate, the cosmic environment. Rockets are also remarkable in how they scale with ambition. A simple-sounding rocket can ascend just tens of kilometers, carrying instruments to measure atmospheric composition or the faintest signals from the upper atmosphere. A human-rated spacecraft, like those that carried astronauts into orbit, must incorporate life support, shielding, guidance, and control systems, all while maintaining structural integrity under extreme acceleration. Lunar missions require propulsion powerful enough to escape Earth's gravity entirely, navigate hundreds of thousands of kilometers of space, and then return safely. These incremental challenges illustrate how the dreams of space travel are deeply intertwined with the realities of engineering, and how human aspiration drives technological innovation, even when the path forward is uncertain. As rocket technology progressed, it became clear that propulsion is not merely about reaching a destination, but about managing time, fuel, and energy in a manner consistent with both physics and biology. Extended missions, whether to lunar orbit or beyond, require careful consideration of trajectory, velocity, and acceleration, with the goal of maximizing efficiency while minimizing risks. Each calculation is informed not only by Newtonian mechanics, but also by experience, observation, and the recognition that space is an environment in which minor errors are magnified, and contingencies must be planned with extraordinary precision. The interplay between human limitation and mechanical performance is a constant theme in rocket design, reflecting the dual nature of these vehicles as both tools and extensions of human intent. It is also worth noting that rockets carry with them a narrative of possibility. They represent not only technical achievement, but the translation of human curiosity into motion. Watching a launch, one cannot help but be aware of the intersection between scientific rigour and imagination. The trajectory traced by the spacecraft is a visible manifestation of countless hours of planning, simulation, and problem solving. Each stage of separation, each burst of acceleration, is the physical realization of calculations, ideas, and years of development. In this way, rockets are a bridge between thought and action, a tangible representation of our desire to explore, to understand, and to transcend the immediate confines of Earth. As propulsion systems evolved, so too did the scope of human aspiration. The first rockets were chemically propelled, relying on combustion of fuel and oxidizer to produce thrust. This method, while effective for short-duration flights and orbital insertion, carries inherent limitations: fuel mass, efficiency, and the diminishing returns of adding more propellant to achieve greater speed. Scientists and engineers began to explore alternatives, including ion drives, nuclear propulsion concepts, and more speculative ideas such as antimatter or fusion-based systems. Each represents a step toward extending the reach of human travel, offering the possibility of moving faster, farther, and with greater efficiency. Yet each also confronts fundamental challenges, from energy requirements to material constraints, highlighting the persistent tension between ambition and reality. The human element of these journeys cannot be understated. Beyond the technical specifications of engines and fuel, rockets are designed to carry life, to protect fragile biological systems in the most extreme environments imaginable. Microgravity, radiation, vibration, and isolation all impose stresses that must be mitigated to ensure not only survival, but functionality. Early orbital flights provided crucial data, revealing how the body responds to weightlessness, how circadian rhythms adjust, and how psychological resilience is tested in confined, isolated environments. The development of rockets is therefore inseparable from the development of life support and human adaptation, illustrating how engineering and biology advance together as humanity reaches for the stars. Even as we consider the limits imposed by propulsion, it is intriguing to think about the cultural and psychological significance of rockets. They embody hope, ambition, and the possibility of transcending the familiar. The sight of a rocket ascending into the sky, leaving behind a trail of flame and exhaust, triggers a deep sense of scale, emphasizing the distance between our terrestrial home and the vastness beyond. Rockets are both functional and symbolic, representing the drive to move outward, to explore, and to redefine what is possible for our species. They are reminders that even the smallest mechanical achievement is part of a broader narrative of curiosity, courage, and persistence. Rockets also illustrate the delicate balance between risk and reward. Launches are inherently dangerous, with failure a persistent possibility. Yet the lessons learned from each attempt, each success and setback, feed into the broader understanding of space travel, informing designs, safety protocols, and mission planning. The process is iterative, incremental, and deeply human, reflecting the understanding that exploration is rarely straightforward. Every successful ascent demonstrates not only technical achievement, but the capacity of humans to persist in the face of uncertainty, to refine, adapt, and extend the boundaries of what is possible. Moreover, the dreams associated with rockets are not limited to physical travel. They inspire imagination, technological innovation, and the pursuit of knowledge across multiple disciplines. Advances in material science, computer modelling, guidance systems, and propulsion have their roots in the challenges posed by rocket travel. Each mission expands the frontiers of human understanding, revealing both the possibilities and constraints of life beyond Earth. Rockets, in this sense, are catalysts for progress, bridging the gap between curiosity and achievement, between the known and the unknown. The path forward is defined not only by propulsion, but also by energy, fuel efficiency, and long-term sustainability. Chemical rockets, while effective for short distances, are insufficient for journeys extending beyond the solar system. Concepts such as nuclear thermal propulsion, ion drives, and fusion engines are actively studied because they promise higher efficiency, longer range, and greater velocity. Each proposal presents its own challenges, engineering, safety, and energy production, that must be overcome to achieve meaningful progress. The interplay between imagination and constraint continues to shape the trajectory of human ambition, illustrating that every dream is measured not only in distance, but in feasibility and preparation. As we consider the development of propulsion and the dreams it enables, it is also useful to reflect on the incremental nature of progress. No single breakthrough eliminates all obstacles. Each advancement builds upon the lessons of the past, incorporating insights from engineering, biology, and physics. Rockets are the tools that translate human vision into motion, but they also serve as experiments in endurance, adaptation, and resource management. The journey from orbit to interplanetary and eventually interstellar travel is composed of countless steps, each dependent upon meticulous preparation, careful observation, and the persistence of both imagination and discipline. And so, rockets are more than machines. They are expressions of a species striving to transcend its immediate environment, balancing the technical demands of propulsion with the biological and psychological requirements of life beyond Earth. They represent hope, risk, and incremental achievement. Each launch, each incremental increase in velocity or distance, carries with it lessons for the future, revealing the constraints that define the absolute limit of human space travel, while simultaneously expanding the horizon of what is conceivable. Rockets are the means by which humans transform possibility into action, and by which dreams become a tangible, measurable, and observable reality. Even as we study the physics of propulsion and the engineering of engines, the dreams embedded in these machines continue to guide the next steps. They remind us that distance is not merely a measurement in kilometers or light seconds, but a reflection of ambition, preparation, and perseverance. The challenges of acceleration, fuel, life support, and navigation are formidable, yet they are approached with a persistent curiosity that defines humanity's engagement with space. Rockets, in their function and symbolism, bridge imagination and reality, creating a pathway toward increasingly distant exploration. And as these technologies continue to evolve, the human imagination remains intertwined with the practical realities of travel. The constraints of mass, energy, and time shape the design of spacecraft, yet the desire to explore drives innovation, pushing boundaries that once seemed immutable. Each development in propulsion technology carries the potential to extend our reach, to reduce travel time, and to sustain human life for longer durations, allowing us to consider destinations that were previously beyond our grasp. The interplay between engineering, biology, and aspiration is the heart of human space travel, and rockets are the vessel through which these elements converge. When humans first set their sights on the moon, it was as if the night sky itself had extended an invitation that was impossible to refuse. Unlike the distant stars, the moon is close enough that we can observe it in detail from Earth, yet distant enough to inspire awe, curiosity, and dreams of presence beyond our immediate world. Its pale face shifting through phases night after night has been a companion to humanity for millennia, quietly marking time, influencing tides, and inspiring myth, poetry, and speculation. The desire to touch it, to leave a human trace on its surface, combines both the practical impulse to explore and the deeply human longing to reach beyond the familiar. The moon is both neighbour and frontier, a destination that reminds us how small we are, yet how bold our curiosity can be. From the earliest observations with telescopes to the first probes orbiting the moon, humans have been gradually familiarizing themselves with its geography, its craters, its maria, and its subtle textures. Each new image, each measurement of terrain and composition has built a mental map, allowing engineers and scientists to plan the delicate operations necessary for a manned landing. Yet these preparations are only part of the story. The moon has always existed as a canvas for human imagination, its silent landscape stark and unchanging in ways that contrast so sharply with the dynamic Earth, encourages contemplation of permanence, solitude, and the subtle interplay of light and shadow. For astronauts, seeing the moon up close transforms it from a distant symbol into a tangible destination, a place with hills and valleys, rocks and dust, waiting to be explored with care and precision. Apollo missions brought this imagination into reality, showing us that the moon is not merely a point of light, but a place that can be walked upon, studied, and understood. Neil Armstrong's first steps, echoed by Buzz Aldrin shortly afterward, became emblematic not only of human achievement, but of the capacity to translate thought and observation into deliberate action. These were tiny steps on a vast, unyielding stage, echoing the same theme as earlier orbital missions, but with a weight and permanence that orbiting alone cannot convey. Each movement across the lunar surface required careful coordination, awareness of the environment, and consideration of the limitations of human mobility in reduced gravity. The moon, with its 1/6 Earth gravity, reshapes the way the body moves, the way balance is maintained, and the way objects are handled. Even something as ordinary as walking becomes an exercise in adaptation, as the body learns to navigate an unfamiliar, almost otherworldly environment. The lunar environment presents challenges that are subtle but profound. Its lack of atmosphere means there is no protection from solar radiation or micrometeoroids, and temperatures swing dramatically between the lunar day and night. Dust, fine and pervasive, clings to equipment and spacesuits, creating unexpected complications for machinery and human comfort alike. Every detail, from the rigidity of a glove to the pressure in a life support suit, must be accounted for in planning lunar exploration. Yet the moon remains accessible enough that humans can live and work there, even briefly, while experiencing the profound isolation and silence that characterize extraterrestrial landscapes. This combination of proximity, risk, and novelty feeds both the practical considerations of travel and the imaginative dimensions of exploration, making the moon an ideal stage for contemplating the possibilities of human expansion into space. Beyond the technical and environmental challenges, the psychological experience of being on the moon has a dimension that cannot be measured by instruments alone. The curvature of the Earth seen from the lunar surface, the stark horizon, the black sky uninterrupted by atmosphere, all contribute to a sense of scale and context that is difficult to communicate in words. Astronauts often describe a profound awareness of fragility and connection, a recognition of both the smallness of human presence and the remarkable capacity to reach distant locations through skill, preparation, and technology. The moon serves as a mirror, reflecting the ambitions and limitations of humanity, while offering a concrete glimpse of what it means to exist beyond Earth. Culturally, the moon has held a persistent place in human consciousness. From ancient myths describing lunar deities and cycles to modern literature and cinema imagining colonies and futuristic settlements, the moon occupies a liminal space between the known and the unknown. Our fascination with it reflects a blend of scientific curiosity and imaginative longing, a desire to place ourselves in environments that challenge our assumptions, test our endurance, and expand our perspective. The Apollo missions, in particular, crystallize this blend, demonstrating that while the moon is physically reachable, it also remains a powerful symbol of possibility, inspiring continued reflection, study, and ambition. The practical lessons of lunar exploration are equally important. The moon has served as a proving ground for technologies that might one day carry humans to more distant worlds. Habitats, life support systems, radiation shielding, mobility equipment, and methods of resource utilization have all been tested or conceptualized in relation to the Moon's environment. Even brief stays provide crucial data on human performance, adaptation to low gravity, and the effects of isolation. In this way, the Moon is both a destination and a laboratory, bridging imagination and experimentation, offering insights that extend far beyond the lunar surface. The reduced gravity also offers a perspective on the human body itself. Bones and muscles respond differently, cardiovascular systems adapt, and even fluid distribution shifts in ways that are instructive for future long-duration travel. Lessons learned on the Moon inform the engineering of spacecraft, the design of exercise regimens for astronauts, and our understanding of what it takes to maintain health in extreme conditions. In essence, the Moon allows us to test the interplay between biological limits and technological solutions, giving us a glimpse into the strategies that will be required for travel to planets and stars far beyond. Even as we consider the Moon scientifically, it is important to note the imaginative horizon it provides. Concepts like lunar bases, resource extraction, and self-sustaining colonies move from science fiction to careful speculation, grounded in observations and the practical realities of lunar conditions. These ideas fuel dreams of further expansion, offering a bridge between what has been achieved and what might be possible in the next decades or centuries. The Moon is close enough that humans can plausibly live and work there with current or near-future technology, yet distant enough to demand innovation, endurance, and vision. It is the first stage in imagining human permanence beyond Earth. The Moon also reshapes our perception of time in space travel. For short-term missions, astronauts experience cycles of light and dark that are markedly different from Earth, with days lasting roughly 29.5 Earth days. Planning activities, managing energy, and maintaining circadian rhythms requires careful consideration of this extended day-night cycle, offering insight into how humans might adapt to other planetary environments or interplanetary travel. These temporal differences, subtle though they may be, influence behavior, cognition, and daily routines, reinforcing the idea that the Moon is both a physical and experiential laboratory. Furthermore, the lunar surface introduces constraints that demand creativity. Mobility is challenging, dust complicates every operation, and communication delays, although small compared to interstellar distances, require planning and patience. These factors remind us that human exploration is an iterative process, combining observation, adaptation, and incremental achievement. Each step taken on the Moon, each experiment performed, is both a practical contribution to knowledge and a rehearsal for more ambitious journeys, offering lessons in persistence, adaptation, and the delicate coordination required for survival in alien environments. In reflecting on the Moon, it is remarkable how imagination and reality intersect. We see it as a poetic neighbour, a glowing presence in the night sky, while simultaneously approaching it as a precise target for scientific inquiry and human activity. Its influence extends beyond immediate exploration, shaping cultural narratives, inspiring technology, and framing the possibilities of future human expansion. The Moon represents both a tangible achievement and a horizon of possibility, allowing us to test the limits of life and technology while feeding the imagination that sustains further ambition. Even as lunar missions have concluded for now, the legacy endures. Robotic missions continue to map the surface, measure composition, and test technologies that might support future human habitation. International interest in lunar exploration is growing, with plans for bases, research stations, and potentially long-term human presence. Each of these endeavours relies on lessons learned from past missions, illustrating how small achievements inform large ambitions. The Moon remains a quiet reminder that even within our nearest cosmic neighbourhood, exploration demands precision, endurance, and an unrelenting curiosity that carries beyond immediate challenges. The imaginative pull of the Moon also serves as a template for distant travel. While Earth's orbit and lunar surface are within reach today, they provide a framework for considering what might be necessary to reach Mars, the outer planets, and eventually stars beyond our solar system. We learn to consider energy requirements, life support, radiation shielding, and human factors in a controlled yet extreme environment. Each step on the Moon is both a concrete achievement and a rehearsal, offering insight into the incremental progression necessary for travel across larger distances and longer durations. And so, the Moon sits between the Earth and the stars, a bridge from familiar home to the vast unknown. Its surface, silent and ancient, reminds us of the fragility of life, the demands of exploration, and the transformative power of perspective. Each footprint left by humans is both a testament to achievement and a symbol of ongoing ambition. Every observation, experiment, and adaptation performed there informs the broader question of human space travel, revealing the constraints, possibilities, and quiet wonder that accompany the act of leaving Earth behind, even briefly, in pursuit of knowledge and presence in the wider cosmos. The Moon, in essence, is where imagination begins to meet practical reality. It teaches patience, persistence, and humility, showing us the precise calculations required to maintain life, while encouraging the audacity to dream of permanent presence beyond our home. It is a testbed, a destination, and an inspiration, illustrating that even the nearest celestial body offers challenges, discoveries, and lessons that ripple outward to inform all subsequent ventures into space, from its silent plains to cratered highlands, from its pale light to the shadows that stretch endlessly across its surface. The Moon provides both the tangible and the symbolic, shaping our understanding of what it means to explore and what it might take to reach ever farther. Beyond the familiar confines of Earth and the quiet presence of the Moon, the solar system stretches outward with a mixture of stillness and subtle motion, a vast expanse filled with planets, moons, asteroids, and the invisible, almost imperceptible currents known as the solar winds. To venture through this region is to encounter a medium that is neither solid nor empty, a space shaped by the continuous flow of particles from the Sun, carrying with it energy, magnetism, and both danger and opportunity for those who seek to travel deeper into the cosmos. Human exploration beyond Earth's orbit has relied on spacecraft that can harness technology and patience, allowing us to move not merely through space, but along these quiet, shifting currents that flow outward from our star. Sailing through the solar winds is less about propulsion, in the traditional sense, and more about understanding the environment, planning trajectories, and adapting to conditions that are subtle yet consequential for every mission. The concept of the solar wind, first proposed and later measured in the mid-20th century, reveals that space is dynamic, even in regions that appear still from Earth. Streams of charged particles, primarily electrons and protons, are constantly emitted from the Sun. Travelling outward at hundreds of kilometers per second, these particles interact with planetary magnetic fields, shape the tails of comets, and create phenomena like auroras, which transform the skies near the poles into dancing lights. For spacecraft, these winds present both challenges and opportunities. On one hand, they can slowly erode surfaces, interfere with electronics, or produce radiation hazards. On the other, understanding these winds allows for optimized trajectories, energy management, and the careful design of instruments to study both the Sun and the interplanetary medium. In this sense, sailing through the solar winds is a lesson in patience, adaptation, and the integration of environmental awareness into the mechanics of motion. Probes such as the Voyagers and Pioneers illustrate how humanity has navigated these winds, not by literal sails but through carefully calculated trajectories that take advantage of gravitational assists, minimal resistance, and the slow accumulation of momentum. Each mission is a careful negotiation with the subtle forces at play, a choreography of movement that allows a small, lifeless machine to traverse billions of kilometers over decades. These robotic explorers carry instruments designed to measure magnetic fields, plasma, radiation, and cosmic particles, providing humanity with insight into regions of the solar system that are otherwise inaccessible. Even without humans on board, these voyages demonstrate the importance of understanding the invisible currents, the energetic flows that define the structure and behavior of space far beyond the comforting envelope of Earth. The concept of using the solar wind itself as a propulsion method has long fascinated scientists and dreamers alike. Solar sails, thin reflective surfaces that harness the pressure of photons emitted from the sun, provide a method of continuous low-thrust propulsion. The idea is elegant in its simplicity. By capturing the momentum of light itself, a spacecraft can gradually accelerate, travelling vast distances over long periods without the need for conventional fuel. This approach has been tested on small scales, with probes successfully deploying solar sails and demonstrating controlled movement, revealing the subtle but effective potential of this method. It is a reminder that human ingenuity often finds ways to work with the environment rather than against it, adapting to conditions that might initially seem hostile or limiting. The regions between planets are far from empty, and the solar wind interacts with interplanetary magnetic fields to create a dynamic and occasionally unpredictable environment. Charged particles can affect electronics, generate currents in conductive materials, and create radiation exposure that, for humans, would pose significant challenges. Understanding these dynamics is essential for planning longer duration missions, whether for robotic exploration or potential human travel beyond Mars. Scientists and engineers use data from previous missions to model the solar wind, predicting fluctuations, particle density, and magnetic field variations, allowing spacecraft to adjust orientation, shield sensitive components, and maintain operational integrity. Sailing through the solar winds is therefore both an act of observation and adaptation, an exercise in patience and strategic planning that mirrors the gradual accumulation of experience and knowledge required for human expansion into space. Beyond the technical and physical challenges, there is the contemplative aspect of moving through this part of the solar system. The distance between planets, the silence punctuated by radio signals travelling for minutes or hours, and the vast emptiness that surrounds spacecraft all contribute to a sense of scale and reflection. Even though these regions are teeming with particles, magnetic fields, and subtle energy flows, they appear to human perception as quiet and still, emphasizing the contrast between our familiar terrestrial environment and the vast, measured expanses of space. Each mission, whether passing near Jupiter, Saturn, or venturing toward the heliopause, highlights the intricate interplay between motion, environment, and the resilience of carefully designed technology. Human ambitions for travel through the solar system also extend beyond current robotic missions. Concepts for crewed journeys to Mars, asteroids, and the outer planets must account for the solar wind, cosmic radiation, and the slow but cumulative effects of prolonged exposure to low-density plasma. Unlike Earth orbit, where the magnetosphere provides significant protection, interplanetary travel exposes humans to a broader spectrum of energetic particles. Shielding, habitat design, and mission timing are all influenced by the behavior of these winds, illustrating that even when motion is largely mechanical or technological, human physiology remains a limiting factor in planning ambitious voyages. Sailing through the solar winds becomes a multi-dimensional problem, combining mechanics, biology, and long-term sustainability. The solar wind also provides insight into the dynamics of the Sun and its interactions with the broader interstellar environment. By studying how these particles propagate, scatter, and interact with planetary magnetospheres, scientists gain understanding of space weather, the heliosphere, and even the transition to interstellar space. Spacecraft moving through these regions become both explorers and observatories, collecting data that informs our understanding of both near and far environments. These insights are critical for imagining human travel beyond the solar system, as they reveal the energetic conditions that spacecraft and astronauts must navigate, and the ways in which subtle forces shape trajectories, equipment, and human safety. Voyager 1, currently the farthest human-made object from Earth, demonstrates the patience required to sail through the solar winds. Launched in 1977, it took years to traverse the outer planets, taking advantage of gravity assists to gain speed, and now drifts at the edge of interstellar space, transmitting faint signals that take over 20 hours to reach Earth. This single probe encapsulates decades of careful calculation, iterative design, and the persistent hope that even tiny human-made objects can extend our reach into regions far beyond immediate perception. The solar wind, the background radiation, and the vast distances all combine to create a setting in which every movement is deliberate and every success is the result of patient coordination between human planning and environmental conditions. In considering the Moon, Mars, and beyond, the lessons of sailing through the solar winds inform every subsequent step. Trajectories must be calculated to maximize efficiency, exposure to radiation minimized, and energy resources carefully balanced. Long-duration missions require careful consideration of psychological, biological, and operational constraints, all while navigating a medium that, though sparse, carries persistent energy flows that influence the motion and safety of spacecraft. In this sense, the solar wind is both a medium to be understood and an obstacle to be navigated, shaping the practical possibilities of human exploration and informing the design of vehicles, habitats, and mission planning. The concept of using the solar wind as a tool, rather than merely a hazard, speaks to a broader principle in human space travel: adaptation. By learning to observe, anticipate, and harness environmental factors, humans expand the scope of what is achievable. Solar sails exemplify this approach, demonstrating that even forces that seem intangible or weak can be exploited for gradual acceleration and trajectory adjustment. These methods may not replace chemical rockets for rapid launches or orbital insertion, but they offer a low-energy method for sustained travel, highlighting how understanding the subtleties of the environment enables incremental expansion into the solar system. At the same time, interplanetary travel is a test of endurance. Voyagers, probes, and potential human missions must operate with minimal intervention over years or decades. Systems must function reliably, with contingencies in place for unforeseen variations in solar activity, particle flux, and electromagnetic conditions. This long-duration perspective emphasizes patience, planning, and adaptation. Sailing through the solar winds is therefore as much a study of temporal endurance as of spatial navigation, teaching lessons about gradual accumulation of distance, energy management, and the delicate balance between risk and resilience. The solar wind also interacts with planetary magnetic fields to create auroras, particle trapping, and subtle environmental effects that, while beautiful, reveal the dynamic nature of space. Human travel must account for these interactions, as radiation exposure can vary based on planetary proximity, magnetic orientation, and solar activity. Even modest deviations in path or timing can affect accumulated exposure, requiring careful modelling and monitoring. The environment, though quiet to the senses, is active and influential, reminding us that space travel is an exercise in patience, observation, and careful planning, in which the apparent stillness belies continuous motion and energetic exchange. As we move further from the sun, the intensity of the solar wind diminishes, but the challenges of distance, isolation, and communication increase. Signals take longer to transmit, resupply becomes impossible, and the margin for error grows ever smaller. Yet these very conditions also provide an environment in which to test endurance, evaluate technology, and plan for human travel to Mars, the outer planets, and beyond. Sailing through the solar winds is both literal and metaphorical, representing the incremental, careful progress necessary to extend presence in space, and the lessons learned here resonate with every future mission. And so, as spacecraft glide through these invisible currents, they carry not only instruments and sensors, but also human ambition, patience, and the capacity for reflection. They teach us that movement through space is not simply a matter of propulsion, but a negotiation with subtle forces, environmental conditions, and the limits of human endurance. Every kilometre travelled, every adjustment in trajectory, every measurement of particles and magnetic fields adds to a growing understanding of the solar system and prepares the way for journeys that may one day carry humans across vast distances beyond the influence of our sun and toward the stars themselves. Even as our spacecraft glide through the solar winds and traverse the space between planets, there emerges a concept that is both tangible and almost impossibly vast: the weight of infinity. It is not a weight measured in kilograms or tons, nor is it something a scale could ever hope to register. Rather, it is the quiet realization of scale, the awareness of distances so immense that ordinary human intuition struggles to comprehend them. To imagine travelling through the solar system is one thing. To consider the distances between stars, to imagine journeys lasting decades, centuries, or even millennia, is quite another. And yet, this weight is part of every reflection on human space travel, subtly influencing both our ambitions and the practical limits that define what we can hope to achieve. Even within our solar system, distances are staggering. The Moon, at roughly 384,000 kilometres away, seems close in comparison to the orbit of Mars, which averages 225 million kilometres from Earth, or Jupiter, more than 778 million kilometres distant. Beyond these, the Kuiper belt stretches for billions of kilometres, and then comes the interstellar void, where even the nearest star, Proxima Centauri, is over 4 light-years away. To put that in perspective, a spacecraft travelling at tens of thousands of kilometres per hour would require tens of thousands of years to reach it. The numbers alone challenge the mind, and yet they are the reality of the environment in which we might one day attempt to travel. The weight of infinity, in this sense, is the accumulation of space, time, and the practical challenges imposed by both. The concept is even more profound when time is factored in. Human perception of duration is shaped by circadian rhythms, attention, and memory, yet these frameworks are calibrated to life on a single planet. When considering interstellar distances, the slow passage of decades can blur, and the scale of human lifespans suddenly becomes almost negligible. The slow accumulation of distance, the incremental progress measured in years or decades, emphasizes that long-duration travel is not merely a technical challenge, but an existential one. It demands consideration of life, reproduction, psychology, and the maintenance of knowledge across spans of time far longer than most civilizations have endured. To sail through the solar system is to confront the fact that the cosmos is vast beyond intuition, and that every step, every calculation, every decision must account for consequences that unfold over generations. Even within the familiar planets of our neighbourhood, the perception of distance can shift dramatically. Travelling from Earth to Mars, for instance, varies with planetary positions. At opposition, the journey may require only hundreds of millions of kilometres, yet when the planets are at their furthest apart, that same journey can be nearly double in distance. The timing of launches, trajectories, and orbital mechanics thus becomes critical, and minor errors in planning can have consequences that are exponentially larger than those experienced in terrestrial travel. The weight of infinity, in this context, is both literal and psychological. Engineers, scientists, and astronauts must internalize the magnitude of the environment while ensuring that every system functions as intended over months of travel. One way to conceptualize this vastness is to consider the speed of light, the universal speed limit that governs all motion in the cosmos. Light travels at roughly 300,000 kilometers per second, yet even at this staggering velocity, the nearest stars are years away. Proxima Centauri, at 4.24 light-years, represents a distance that would take tens of thousands of years to traverse using current chemical propulsion. The human mind struggles to reconcile these scales with the everyday perception of travel, yet the universe imposes them nonetheless. The weight of infinity, then, is a combination of distance, time, and the limitations imposed by fundamental physics. It reminds us that even our most ambitious plans for travel are constrained by realities that are immovable, unyielding, and profoundly humbling. Beyond distance, the weight of infinity also manifests in the resources required to sustain life over extended periods. For human space travel, energy, fuel, food, water, and protection from radiation become exponentially more demanding as missions extend in distance and duration. Carrying sufficient resources for even a single-year journey to Mars challenges current engineering, and extending these missions into multi-generational interstellar voyages introduces complexities that are almost unimaginable. Every kilogram of mass requires additional fuel to accelerate, maintain, and decelerate, creating a cascading effect in which the requirements for life support, propulsion, and structural integrity grow in proportion to distance. The weight of infinity is thus both conceptual and practical, influencing mission design, human adaptation, and the strategies we must employ to survive beyond the bounds of our planet. Even unmanned exploration highlights the scale in striking ways. Consider the Voyager spacecraft, launched in 1977, now drifting in interstellar space. It has travelled tens of billions of kilometres, yet it has only just begun to exit the heliosphere, the bubble of influence created by the Sun. Signals from Voyager take more than 20 hours to reach Earth, and its instruments, though still functioning, rely on a source of energy that diminishes slowly over time. The persistence of this small probe emphasizes how even modest steps through the cosmos require patient, careful planning and acceptance of the limitations imposed by distance, energy, and the passage of time. The weight of infinity is evident in these missions, which unfold over decades, highlighting both the remarkable endurance of human design and the challenges posed by the vastness of space. Beyond physical distance and energy, the weight of infinity carries psychological implications. Humans are creatures whose perception of scale, risk, and duration is grounded in terrestrial experience. To consider journeys spanning decades, centuries, or generations requires recalibration of perspective. Time for the traveller, time for those remaining behind, and time relative to distant destinations all become entangled. Concepts such as multi-generational ships, suspended animation, and life in artificial habitats emerge not only from technological necessity, but from the human need to reconcile ambition with the unyielding scope of the cosmos. The weight of infinity is therefore both external and internal, shaping engineering and imagination, preparation and expectation, endurance and perception. Even as we consider the enormity of space, it is worth noting that our understanding is continually refined by exploration, observation, and calculation. Planetary probes map surfaces, track orbits, and measure environments. Telescopes provide ever more detailed perspectives of stars, nebulae, and distant galaxies. These efforts reduce uncertainty, reveal patterns, and allow predictions that guide mission planning. Yet the fundamental vastness remains, reminding us that scale is a central challenge in human space travel. Every observation, every calculation, and every technological advance contributes to our ability to navigate and survive in environments where distances are measured not in familiar units of time or speed, but in years, decades, and lifetimes. In reflecting on the Moon, Mars, and the outer planets, it becomes evident that the limits of human space travel are defined not only by propulsion and life support, but by the cumulative effects of distance, duration, and the weight of infinity. Each incremental achievement, from orbit to landing to extended exploration, contributes to a growing understanding of what is possible. Even as our ambitions extend toward interstellar travel, the principles remain the same: careful planning, incremental adaptation, and a persistent awareness of scale. The weight of infinity is ever present, guiding decisions, shaping strategy, and framing the possibilities of what humans might accomplish in the vast reaches beyond our planet. The vast distances also amplify the challenges of communication and control. Signals between Earth and Mars, for example, experience delays of up to 20 minutes, making real-time guidance impossible. As missions extend to the outer planets or beyond, these delays increase to hours, days, or even months, requiring autonomy, robust planning, and redundancy in both systems and decision-making processes. The weight of infinity is felt not only in the physical travel required, but in the operational frameworks necessary to manage complex tasks over incomprehensible spans of space and time. Even beyond interstellar ambitions, the solar system itself offers a striking illustration of scale. Jupiter, with its enormous gravity well, challenges trajectory planning and fuel allocation. Saturn, with its rings and multiple moons, adds further complexity. The Kuiper Belt and Oort cloud extend for billions of kilometers, offering potential sources of material for future missions, but also imposing additional considerations for navigation and survival. Every region of the solar system reveals new facets of the weight of infinity, highlighting both the opportunities for discovery and the constraints that define the boundaries of human reach. And yet, in contemplating this vastness, it becomes clear that human ambition persists. Engineers, scientists, and dreamers alike continue to explore ways to extend travel, from propulsion systems that maximize efficiency to concepts like generational ships, hibernation, and solar sails. These approaches recognize that while the cosmos imposes limits, ingenuity, adaptation, and patience provide pathways to meaningful exploration. The weight of infinity is not a barrier to imagination. Rather, it defines the framework within which dreams and practical solutions must operate. Even as we look forward, the psychological experience of confronting the infinite remains profound. Astronauts, scientists, and casual observers alike are struck by the scale of space, the subtlety of its motions, and the interplay of distance, light, and time. The cosmos is at once vast and comprehensible through careful observation, yet it constantly challenges perception and expectation. Human space travel in this sense is both a technical and existential pursuit, requiring awareness of the limits imposed by physics, biology, and duration, while maintaining the capacity to imagine what might lie beyond immediate observation. The weight of infinity also shapes ethical and philosophical considerations. Long-duration missions, multi-generational voyages, and interstellar ambitions raise questions about responsibility, planning, and the well-being of those who may spend entire lifetimes in transit. Decisions about resource allocation, habitat design, and mission goals must account for human health, psychological stability, and societal continuity over spans far exceeding typical human experience. In this context, the vastness of space is not merely a physical challenge, but a test of foresight, planning, and humanity's ability to adapt to environments where scale and duration redefine everyday assumptions. As we contemplate the vast distances between planets, stars, and beyond, a fundamental principle becomes impossible to ignore. The universe has a speed limit. Unlike any speed humans typically experience on Earth, this cosmic ceiling is absolute, universal, and unyielding. It is the speed of light, travelling at roughly 300,000 kilometers per second, a constant that shapes not only how we observe the cosmos, but the very limits of how far and how fast humans could ever travel. To sail through the solar system, to imagine reaching other stars, is to confront this boundary directly. No matter how advanced our propulsion systems become, no matter how much ingenuity or energy we can muster, we're ultimately constrained by this universal limit. And yet, there is a quiet beauty in this realization. a recognition that the cosmos is structured in a way that defines both possibility and perspective. For humans, moving at familiar speeds, cars, planes, rockets, rarely gives a sense of the enormity of this limit. A spacecraft travelling at tens of thousands of kilometres per hour may seem impossibly fast in daily life, yet it is only a fraction of the speed required to approach light-speed travel. The difference between our terrestrial experiences and the constraints of the universe highlights the profound gap between human perception and cosmic reality. Even the fastest missions to the outer planets are still slow by comparison, taking years to reach distances that, in cosmic terms, are relatively small. The speed limit of the universe is a reminder that distance and time are inseparable when planning human travel beyond the confines of the solar system, and that our ambitions must align with the fundamental structure of reality itself. The implications of the speed of light extend beyond mere travel time. According to Einstein's theory of relativity, as an object approaches this speed, time itself begins to behave differently. Clocks on board a near-light-speed spacecraft tick more slowly relative to observers remaining at rest, an effect known as time dilation. For a human traveller, decades could pass in the external universe while only a few years are experienced on board. This is not science fiction, but a consequence of the physics that govern space-time. The universe imposes both limits and curiosities on travel, revealing that distance and speed are not independent, but deeply intertwined with the passage of time and the experience of motion. The challenge, then, is not only engineering propulsion capable of reaching substantial fractions of light speed, but also understanding the biological, psychological, and logistical implications of time dilation. For long-duration missions, even small differences in experienced time can affect communication, coordination, and mission planning. Signals travelling between the spacecraft and Earth would arrive with delays that grow longer with distance, requiring autonomy, redundancy, and precise timing to ensure that operations remain synchronized. The speed limit of the universe thus transforms human space travel into a multi-dimensional problem, where velocity, time, energy, and life support are inseparably linked. Even within our solar system, approaching light-speed velocities presents challenges that are far beyond our current technology. Chemical rockets, nuclear thermal propulsion, and ion drives all rely on expelling mass to generate momentum, yet the energy required to accelerate a human-scale vessel to relativistic speeds is enormous. The mass-energy equivalence expressed by Einstein's famous equation, E equals mc squared, underscores the fundamental limits imposed by nature. As velocity increases, so too does the energy required to continue accelerating, approaching infinity as the speed of light is approached. This is not merely a practical limitation, but a fundamental feature of the universe, a rule that no amount of engineering can override. Even the smallest spacecraft would require energy levels that are currently inconceivable to achieve relativistic speeds, demonstrating that human ambition is bounded not only by imagination, but by the laws of physics themselves. Yet the universe's speed limit also provides opportunities for understanding and creativity. While we may not be able to reach light speed, careful planning of trajectories, utilization of gravitational assists, and exploitation of natural currents such as the solar wind allow us to maximize the efficiency of travel within the constraints imposed by reality. Each mission, whether robotic or crewed, requires optimization of energy, mass, and time to achieve goals while respecting the universal limit. The speed of light is not merely a barrier, it is a framework that guides design, strategy, and expectation, informing the way we approach every journey beyond Earth. Even speculative concepts such as the idea of warp drives rely on an understanding of the speed limit. The Alcubierre drive, a theoretical proposal, would contract space in front of a spacecraft and expand it behind, allowing effective faster-than-light travel without locally exceeding the speed of light. While entirely hypothetical and currently beyond practical engineering, These concepts illustrate the human desire to explore, to overcome limits, and to envision possibilities that stretch both imagination and physics. Even when constrained by absolute rules, humans consider ways to navigate, adapt, and creatively engage with the boundaries of what is possible. The speed limit of the universe, in this way, becomes not only a constraint, but a canvas for intellectual exploration, a structure within which imagination can safely roam. It is also striking to consider how the speed of light shapes communication. In interstellar travel, signals cannot exceed this limit, meaning that messages between Earth and a distant spacecraft would take years to arrive. This has profound implications for mission design, autonomy, and planning. For example, even if a crewed vessel were capable of travelling to the nearest star over decades, real-time communication with Earth would be impossible. Decisions would need to be made independently, relying on onboard judgment, predictive models, and prior knowledge. The speed limit thus transforms not only motion, but interaction, forcing humans to reconcile the desire for connection with the reality of cosmic separation. The practical effects of this limit are also visible in our robotic exploration. Voyagers, New Horizons, and other long-distance probes travel at fractions of light speed, yet still require years or decades to reach their targets. Signals take hours to traverse distances within the solar system, and years to cross interstellar gaps. Planning these missions involves accounting for cumulative delays, energy budgets, and redundancy, highlighting how the speed of light imposes both temporal and operational boundaries. Even as technology improves, the fundamental limit remains, guiding expectations, calculations, and timelines for exploration. Time dilation at near light speed introduces a deeply human dimension to space travel. For travelers, subjective experience may differ dramatically from external observers. While years might pass on board, decades or centuries could unfold on Earth. This disparity raises not only technical challenges, but philosophical questions. How do humans maintain connection with those left behind, plan for generational continuity, or reconcile the passage of time with personal experience? The speed limit of the universe thus influences psychology, culture, and human perception, reminding us that travel is not merely a matter of engineering, but also of adaptation to fundamental realities that extend far beyond immediate intuition. Even as we acknowledge these limitations, the speed of light serves as a guidepost for ambition. We learn to measure distances in terms of light years, to plan trajectories with an understanding of relativistic effects, and to design missions that optimize motion within an unalterable framework. The speed limit emphasizes that human reach is inherently constrained, yet it also inspires ingenuity, careful planning, and creativity in seeking ways to extend presence as far as feasible. Each mission becomes both an exercise in patience and a testament to the human capacity to navigate within limits, while imagining possibilities beyond them. Considering propulsion again, it becomes evident that energy requirements grow dramatically as velocity increases. Rockets rely on expelling mass to accelerate, and as speeds approach relativistic fractions of light, the mass energy demand approaches impracticality. For a spacecraft designed to carry humans, the energy required to reach even 10% of light speed is extraordinary, demanding technologies, fuels, and efficiencies that are currently beyond our capacity. These calculations reveal the interplay between ambition, physical laws, and practicality, showing that the absolute speed limit is not only theoretical, but a critical constraint that shapes planning for human expansion into space. Even with unmanned exploration, the speed of light constrains observation. Telescopes detect light that may have travelled years or even millennia to reach us, meaning we always see the universe in the past. This delay emphasizes that motion and perception are linked. Speed is not just about reaching destinations, but also about acquiring knowledge in a timely manner. Planning for human space travel requires similar awareness, understanding how temporal and spatial scales interact, predicting trajectories, and anticipating the consequences of movement through an environment constrained by an absolute speed. The speed limit also emphasizes the importance of patience and incremental progress. Rather than attempting impossible leaps, human exploration has advanced through careful accumulation of experience, technological improvement, and adaptation to the environment. Orbital missions, lunar exploration, and robotic missions to the outer planets all reflect this approach, demonstrating that even within universal limits, meaningful progress can be achieved. The constraints imposed by light-speed travel become a framework within which ambition is realized, not negated, guiding the pace, scale, and expectations of every journey. The speed limits of the universe are simultaneously restrictive and instructive. They define the bounds of motion, shape our understanding of time, and influence every aspect of mission planning. Yet within these limits, human ingenuity finds pathways, whether through careful trajectory planning, autonomous operation, or speculative concepts like warp drives. The speed of light serves as both constraint and inspiration, a constant that anchors our understanding of space, while allowing imagination to explore strategies for extending human presence as far as is practically possible. As we consider the constraints imposed by the speed of light and the vast distances of the cosmos, another fundamental factor comes into focus: energy. Every motion through space, every incremental push forward, every attempt to bridge the gulf between stars requires energy in a precise, almost unforgiving sense. Human travel beyond Earth is not simply a matter of desire or imagination, it is a matter of supply, calculation, and endurance. The rocket engines that lift a spacecraft off the ground convert fuel into thrust, but the relationship between mass, velocity, and energy is relentless. Adding more fuel increases weight, which in turn demands more energy to accelerate, creating a delicate balance that becomes ever more pronounced as ambitions extend toward other planets, the outer solar system, or distant stars. Understanding these constraints is essential for any realistic exploration of the cosmos, revealing the limits of what humans can achieve with current technology and the incremental innovations necessary to extend those limits. Even within the solar system, energy management is a subtle challenge. A mission to Mars, for instance, requires not only energy to escape Earth's gravity, but also the energy to correct trajectory, maintain life support, and maneuver in orbit around the destination planet. Each kilogram of payload, whether it is scientific instruments, supplies, or humans themselves, demands additional fuel, and every maneuver must be carefully calculated to conserve energy while maximizing efficiency. These considerations are magnified when thinking about more distant targets. As travel distances grow, so too does the energy required, and the practical limitations of carrying enough fuel become starkly apparent. Energy, in this context, is not an abstract concept but a concrete measure of possibility, shaping both mission design and human ambition. The human body itself imposes additional constraints on energy. Unlike robotic spacecraft, which can function under extreme conditions with minimal maintenance, humans require food, water, air, and shelter to survive. Each of these necessities requires energy to produce, store, and transport. The longer a mission, the greater the cumulative requirement for life-sustaining resources. Even advanced systems that recycle water, grow food, or manage waste cannot eliminate these demands entirely. They can only reduce the burden slightly. Extended travel becomes a careful exercise in resource allocation, balancing propulsion, sustenance, and environmental control. The limits of human endurance intersect with physics, forming a boundary that technology can approach but never completely circumvent. Fuel efficiency is another critical consideration. Traditional chemical rockets are effective for short bursts, launching payloads into orbit and beyond, yet they are constrained by the energy density of the fuel they carry. To reach velocities approaching significant fractions of the speed of light, current chemical propellants are insufficient. Nuclear thermal propulsion, ion drives, and other advanced concepts offer alternatives, but each presents its own challenges in energy management, safety, and scalability. Even if propulsion could theoretically achieve higher velocities, the energy required to sustain human life over the course of the journey adds additional layers of complexity. Energy is never merely an abstract quantity. It is the medium through which distance, velocity, and survival are reconciled. Radiation is an additional energy-related constraint that cannot be overlooked. Beyond Earth's protective magnetosphere, high-energy particles from the sun and cosmic rays constantly bombard spacecraft, posing risks to both electronics and biological systems. Shielding against this radiation requires additional mass, which in turn demands more fuel, which in turn demands more energy to accelerate. Each layer of protection, each redundancy added to ensure survival, accumulates in weight, demonstrating how energy, mass, and human limits are intertwined. The cosmos is not a passive medium. It imposes energetic and physical challenges that shape the practical ceiling of human travel. Life support systems themselves are energy intensive. Maintaining temperature, air pressure, and oxygen levels in the vacuum of space requires continuous input, while water recycling, food preparation, and waste management all consume additional resources. Even minimal inefficiencies in these systems can have cumulative effects over long durations, highlighting the importance of precise engineering, careful monitoring, and redundancy. The energy required to sustain life becomes inseparable from the energy required to propel the spacecraft, revealing a fundamental constraint that links physics and biology inextricably. Energy also shapes the psychological and social dimensions of travel. Human inhabitants of spacecraft require not only sustenance but stimulation, comfort, and a sense of continuity. Lighting, climate control, communications, and exercise all require power. Without sufficient energy allocation, the physical and mental well-being of travelers becomes compromised, potentially jeopardizing the mission. The constraints of energy are therefore not only mechanical, but profoundly human, shaping how life is experienced, how time is perceived, and how endurance is maintained in environments that are fundamentally hostile to terrestrial life. Long-duration missions to distant worlds introduce additional challenges. The farther a spacecraft travels, the more it must rely on onboard energy sources, whether solar, nuclear, or otherwise. Solar energy diminishes with distance from the Sun, requiring alternative solutions for missions to the outer planets or beyond. Nuclear sources offer consistent energy output, but introduce concerns about safety, radiation, and heat management. Each choice has trade-offs that must be carefully considered, and the cumulative effect of energy limitations imposes practical ceilings on mission duration, payload capacity, and velocity. The constraints are simultaneously subtle and relentless, emphasizing that human travel through space is an intricate negotiation between ambition and the fundamental laws of physics. Even the most advanced proposals for interstellar travel confront these same principles. Concepts such as fusion propulsion, antimatter drives, or large-scale solar sails all rely on energy densities far beyond what is currently achievable with known technology. The challenge is not merely to generate enough energy for propulsion, but to balance that energy against life support, communication, navigation, and structural integrity. Every increase in energy allocation for propulsion reduces the energy available for sustaining humans and maintaining systems, illustrating a zero-sum game in which limits are inescapable. The absolute boundaries of human space travel are, in this sense, framed as much by energy considerations as by velocity, distance, or biological limits. Psychology interacts with these constraints in subtle ways. The awareness of energy limitations, resource scarcity, and the impossibility of immediate resupply can weigh heavily on human travelers. Planning, rationing, and careful decision-making become essential, not only to ensure survival, but to maintain morale and cognitive function. The energy budget is therefore both a physical and psychological framework, shaping behavior, perception, and the ability to endure extended isolation. Human limits are intertwined with energy availability, making the careful allocation and management of resources a central aspect of any serious consideration of space travel. Beyond physical energy and fuel, there is also the energy of knowledge and calculation. Every maneuver, trajectory correction, and decision requires cognitive resources, careful measurement, and continuous observation. The allocation of attention, the accuracy of prediction, and the capacity to respond to unexpected changes consume a form of intellectual energy that is inseparable from physical energy. Human travel through space, therefore, is not only a mechanical challenge but a mental and social one, requiring coordination, foresight, and the ability to adapt to environments that are at once predictable and uncertain. Even minor miscalculations in energy management can have disproportionate consequences. A small error in propulsion, navigation, or resource allocation can cascade into larger problems, delaying arrival, reducing efficiency, or compromising safety. The weight of energy, in this sense, is cumulative. It is not a static resource, but a dynamic measure of planning, execution, and adaptability, reflecting both the precision required in engineering and the limitations inherent in human endurance. Every watt, kilogram, and calculation matters, illustrating the interplay between ambition and constraint that defines practical human travel in space. As we consider these factors, it becomes clear that energy, fuel, and human limits are intertwined. They define the feasible scope of travel, shape mission duration, and influence every technological choice. Rockets, solar sails, nuclear engines, and even theoretical propulsion systems all operate within this framework, constrained by the unyielding requirements of physics and biology. The dream of reaching distant stars must be reconciled with the practicalities of sustaining life, managing resources, and ensuring safety over time spans and distances that dwarf terrestrial experience. Energy becomes both the enabler and the limiter, the measure by which we assess the possibility of human exploration. Even incremental achievements illustrate these principles. Orbital missions, lunar landings, and robotic explorers all require careful calibration of energy inputs for propulsion, life support, and instrumentation. These missions highlight that travel is not solely a matter of ambition or imagination. It is a complex orchestration in which every action consumes energy and every decision carries consequence. The careful balance of energy, fuel, and human needs is therefore central to planning, execution, and evaluation of space travel. The absolute limits of what humans can achieve are defined not only by velocity or distance, but by the finite and non-negotiable requirements of sustaining life in environments that are fundamentally hostile to terrestrial existence. In reflecting on these constraints, it is worth noting the interplay between technological advancement and human adaptation. Every improvement in fuel efficiency, propulsion design, or energy generation expands the envelope of possibility, yet the underlying limits remain. Humans require sustenance, protection, and environmental stability. Spacecraft require energy for navigation, communication, and operation. Every additional kilogram of fuel, food, or shielding increases the energy required to accelerate and sustain motion. The constraints are not abstract. They are a continuous interacting system that defines the boundaries of practical achievement. The careful consideration of energy, fuel, and human limits also informs long-term planning for exploration beyond the solar system. Generational ships, cryogenic preservation, and autonomous habitats all address the challenge of sustaining life over durations that exceed what can be supported by conventional propulsion and energy resources. Even these theoretical solutions highlight the delicate balance required. Every system consumes energy, every life requires sustenance, and every motion requires power. The weight of these requirements accumulates, illustrating that the absolute limit of human travel is as much about survival as it is about propulsion. Surviving in the void of space is an exercise in constant vigilance, a delicate negotiation between human fragility and the unforgiving environment beyond our planet. Once we leave the protective envelope of Earth's atmosphere, every breath, every drop of water, every calorie consumed becomes a carefully managed resource. The vacuum outside a spacecraft is silent and cold, yet it is lethal in the absence of shields and support systems designed to replicate in miniature the conditions humans need to survive. Life support is not simply a convenience, it is the invisible scaffolding that allows exploration to occur, the unseen network that transforms metal, electronics, and plastic into a temporary home capable of sustaining life in an environment where even a minor failure could have catastrophic consequences. Air, the most immediate necessity, demands careful management. In the microgravity of orbit or during transit to distant worlds, oxygen must be generated, circulated, and replenished with extreme precision. Early spacecraft relied on compressed oxygen tanks and chemical systems that could scrub carbon dioxide from the air. Modern systems incorporate electrolysis, splitting water into hydrogen and oxygen, allowing for continuous recycling of a closed atmosphere. Even slight deviations in oxygen concentration can affect cognition, mood, and physical performance, so monitoring is continuous and precise. The act of breathing, so automatic on Earth, becomes a carefully engineered part of life in the void, highlighting how intimately human survival is tied to technology when the familiar protections of our planet are absent. Water, another fundamental necessity, presents its own complex challenges. Unlike oxygen, which can be generated from onboard systems, water requires careful conservation, recycling, and storage. Closed-loop systems reclaim moisture from respiration, perspiration, and even waste, purifying it to be reused for drinking, food preparation, and hygiene. The energy cost of these processes is non-trivial, emphasizing the interconnected nature of life support. Propulsion, electricity, temperature control, and chemical systems all converge to ensure the simplest acts, drinking, washing, and breathing, are possible. A spacecraft is a machine designed not only to move through space, but to mimic the protective conditions of Earth with meticulous precision. The margin for error is small, and even minor inefficiencies accumulate over long-duration missions. Temperature regulation is another invisible requirement for life in space. Outside a spacecraft, temperatures fluctuate wildly depending on exposure to the sun, and even small deviations can be fatal. Inside, life support systems carefully monitor and adjust heating and cooling to maintain a consistent habitable environment. Microgravity complicates this further, as convection, the movement of heat through air, is altered, requiring fans, ducts, and precisely calculated airflow patterns to ensure uniform temperature distribution. Without this control, localized heating or cooling could create zones unsafe for human occupancy, or stress systems in unexpected ways. Every component of life support, from air circulation to thermal control, is interdependent, forming a network that keeps humans alive in a place that is otherwise completely inhospitable. Nutrition and food storage, too, are shaped by the demands of the void. Fresh food cannot accompany long-duration missions beyond Earth, so astronauts rely on preserved, compacted, and nutritionally balanced provisions. The choice of food affects not only sustenance, but morale, comfort, and the maintenance of healthy microbiomes. Growing food in space through hydroponics or other experimental systems introduces additional energy and resource demands, yet it offers a glimpse into the long-term possibilities for sustaining human life on distant worlds. The design of these systems illustrates how life support extends beyond immediate survival, encompassing the holistic needs of human existence, including psychological well-being and the subtle pleasures of taste, texture, and variety. Radiation protection is another critical aspect of life support, particularly as humans travel beyond low Earth orbit. Cosmic rays, solar particle events, and high-energy radiation pose significant health risks, from increased cancer probability to damage to the central nervous system. Spacecraft must incorporate shielding, structural barriers, and carefully planned exposure schedules to mitigate these hazards. Even with protective measures, the risk is never entirely eliminated, emphasizing that life in space is a constant negotiation with forces that we cannot control, only anticipate and minimize. The experience of humans in these conditions requires both engineering and psychology, as the knowledge of danger becomes part of everyday existence and decision-making. Waste management is a topic that is often overlooked in casual considerations of space travel, yet it is fundamental to the integrity of life support systems. Every human produces waste, both biological and material, and in a closed environment, it cannot simply be discarded. Systems must capture, treat, and recycle or store waste safely to prevent contamination, maintain hygiene, and support recycling of essential resources such as water. The design of these systems demonstrates the intricate balance required to sustain life. Even seemingly minor details, such as the placement of a toilet or the routing of air vents, can have cascading effects on habitability, efficiency, and health. Life support in the void is as much about meticulous planning and redundancy as it is about engineering and material science. Psychological well-being is as critical as physical survival. Isolation, confinement, monotony, and distance from familiar social networks create stresses unique to space travel. Life support systems must account for these factors, providing lighting cycles to mimic circadian rhythms, communication links to Earth, opportunities for exercise, and spaces that allow privacy and autonomy. Maintaining mental health is inseparable from maintaining physical health, and every subsystem contributes to an environment where humans can function effectively over long durations. The void is indifferent, yet it shapes human experience profoundly, emphasizing that life support is not merely technical but deeply human-centered. Even small perturbations in life support can have amplified consequences over long-duration missions. A minor failure in air circulation, water recycling, or thermal regulation can escalate into serious threats if not detected and corrected quickly. Redundancy, monitoring, and emergency procedures are therefore critical, illustrating that sustaining life in the void is a constant vigilance rather than a static state. The environment outside the spacecraft is not forgiving. It imposes continuous demands, and human survival depends on the seamless integration of numerous systems, careful attention to detail, and the anticipation of contingencies. As missions extend farther, whether to Mars, the outer planets, or even the edges of the solar system, the energy requirements for life support grow in parallel with propulsion demands. Every resource consumed, every system operated, every contingency prepared requires energy, creating a direct link between life support and the technical feasibility of long-distance travel. Human limits are therefore inseparable from the design and efficiency of life support systems, highlighting the interdependence of biology, engineering, and physics. Energy is never simply a measure of propulsion. It is the foundation of survival itself. Even the smallest innovations in life support can have profound implications for mission success. Advances in recycling, oxygen generation, water purification, and waste management incrementally extend the duration and distance over which humans can travel. Each improvement may seem minor in isolation, but together they create a cumulative capacity for extended exploration. Life support is therefore both an engineering challenge and a continuous project of refinement, a reflection of the careful, deliberate accumulation of knowledge and adaptation that characterizes human expansion into space. Consider too the balance between automation and human oversight. Life support systems are largely automated, with sensors and algorithms maintaining optimal conditions, yet humans remain essential for monitoring, troubleshooting, and adapting to unforeseen circumstances. The interplay between machine and human operator underscores the complexity of survival in the void, highlighting that life support is not a passive system, but an active partnership between technology and its inhabitants. Every adjustment, every calibration, and every observation contributes to the stability of the environment, reinforcing the idea that survival is a dynamic, ongoing process rather than a static guarantee. Even as exploration moves toward more distant targets, life support becomes increasingly integrated with other aspects of mission design. Shielding, habitat design, propulsion efficiency, energy management, and crew health all converge in a network of interdependent considerations. The void of space amplifies the consequences of inefficiency, error, or oversight, meaning that life support is inseparable from the broader planning and execution of any journey. The careful orchestration of these systems is a testament to human ingenuity, patience, and the ability to transform inhospitable environments into places capable of sustaining life, even temporarily. The complexity of life support also reflects the inherent fragility of human life in space. Unlike machines, humans cannot simply pause metabolism, eliminate oxygen consumption, or withstand prolonged radiation without consequence. Every physiological process is sensitive to environmental conditions, and every system failure, however minor, carries potential consequences. This fragility underscores the importance of redundancy, monitoring, and careful design, as well as the ongoing development of new technologies to extend human endurance. Life support is thus both a technical challenge and a reflection of our understanding of human biology, integrating knowledge across disciplines to create an environment in which humans can persist in otherwise impossible conditions. Ultimately, life support in the void is a demonstration of the intricate interplay between human limitations, engineering solutions, and the environment. It is not simply a series of machines and procedures, but a comprehensive framework that sustains life, enables exploration, and allows humans to extend presence beyond the protective confines of Earth. Every breath, every drop of water, every controlled temperature gradient reflects careful planning, meticulous design, and a deep awareness of both human needs and the unforgiving nature of space. The void itself is indifferent, yet through life support it becomes navigable, survivable, and even, in a sense, habitable. Travelling beyond the solar system is a journey measured not in days or months, but in decades, and even centuries. The idea of sending humans to distant stars forces us to confront an entirely new dimension of planning, one where the individuals who leave Earth may never see the destination themselves. Generational ships, vessels designed to sustain multiple human lifetimes, emerge as a necessary concept when considering these extreme distances. They are not simply spacecraft. They are entire self-contained worlds, miniature ecosystems where life, reproduction, education, and culture must be maintained for decades or centuries without external resupply. Every system, every procedure, and every structure must function with extraordinary reliability, because failure affects not just a mission, but the survival of generations born and raised aboard the vessel. The challenges of a multi-generational journey begin with population management. Maintaining a stable, genetically diverse population requires careful planning, balancing the number of individuals, reproductive cycles, and genetic considerations to avoid inbreeding or demographic collapse. Food production, medical care, and education must be sustained across lifetimes, each generation learning to maintain the systems built by the previous one. Unlike missions of a few months or years, these voyages demand that human culture, social structure, and governance be carefully thought out and resilient to the slow erosion of time. The vessel becomes both a laboratory and a society, a place where survival, psychology, and social cohesion are as important as propulsion and energy management. Maintaining psychological health across generations is equally critical. Isolation from Earth, the confined environment of a spacecraft, and the absence of familiar natural rhythms impose unique stresses. Humans rely on sensory input, social interaction, and variety in environment to maintain mental well-being. Generational ships must incorporate opportunities for recreation, education, and cultural expression, creating spaces that feel dynamic rather than sterile. The ship becomes more than a machine. It is a home, a community, and a nurturing environment for human development over multiple lifetimes. Designers must consider how humans will experience space, not as a temporary adventure, but as a permanent context for existence. The architecture of such a vessel is intertwined with its function. Life support, energy systems, waste recycling, and food production must operate continuously, often autonomously for centuries. Redundancy is essential, as is the ability to repair or reproduce critical components with limited materials. Advances in automation, artificial intelligence, and resource management become integral to survival. Humans will live, learn, work, and age within this engineered environment, relying on the systems around them as they might rely on Earth itself, yet with far less tolerance for error. The design of a generational ship must therefore balance engineering precision, energy efficiency, and human needs over extraordinarily long durations. Every decision about travel also becomes a reflection of risk management. Life aboard a generational vessel is subject to the hazards of space, radiation, micrometeoroid impacts, system failures, and the psychological strain of the long-term confinement. Mission planners must account for contingencies that could affect not just individuals, but entire cohorts. Redundancy in critical systems, emergency protocols, and robust social structures are necessary to mitigate these risks. The scale of planning is almost unimaginable. Decades of preparation, centuries of maintenance, and an understanding that even minor oversights can propagate consequences over generations. This perspective highlights the unique challenges posed by human space travel when time stretches beyond a single lifetime. Education and knowledge transfer are essential components of sustaining life on a multi-generational ship. Children born in transit must learn not only the skills required to maintain the vessel, but also the understanding of why these systems exist. Institutional memory cannot rely solely on technology. Human understanding and adaptability are essential. Training programs, cultural transmission, and mentoring systems must be robust, allowing knowledge to be retained, adapted, and improved with each successive generation. Without careful attention to these elements, the mission risks both practical and cultural collapse, demonstrating that human space travel over centuries is as much about sociology as engineering. Nutrition and resource management are ongoing challenges in this context. Unlike short missions where resupply is feasible, multi-generational vessels must produce and recycle almost everything on board. Hydroponics, aquaponics, and closed-loop systems become necessary for sustaining life. Crop diversity, energy efficiency, and waste recycling must be balanced to meet the needs of multiple generations while preserving the stability of the environment. Even minor disruptions in food production can cascade, affecting physical health, mental resilience, and social cohesion. Life aboard a generational ship is therefore a continuous balancing act, integrating biology, engineering, and community planning into a single coherent system capable of surviving the slow march of time. The human body itself must adapt to long-term microgravity or reduced gravity environments. Bone density loss, muscle atrophy, cardiovascular adjustments, and sensory changes all challenge the maintenance of health across generations. Solutions may include artificial gravity, rotational habitats, or carefully managed exercise regimens. Each intervention requires energy, space, and infrastructure, reinforcing the interconnectedness of physical and social systems. Generational voyages are thus a synthesis of biological, technological, and cultural adaptation, highlighting the ways in which human limitations define and are defined by the environments we create. Social cohesion presents its own set of challenges. Over multiple generations, maintaining harmony, preventing conflict, and fostering cooperation are essential for survival. Governance structures, social norms, and conflict resolution mechanisms must be embedded in the culture of the ship. Planning for generational continuity is not simply about technical survival. It is about sustaining a society capable of functioning effectively over centuries under conditions that would strain even the most resilient human communities on Earth. These social considerations underscore the unique complexity of human space travel when extended across lifetimes, demonstrating that technical achievement alone is insufficient to ensure success. Ethical considerations are also profound. Decisions about reproduction, resource allocation, and long-term planning carry consequences for individuals who may never consent to being born in transit. Mission designers must weigh the rights and well-being of future generations against the ambitions of the present. These moral questions are inseparable from the technical and practical aspects of generational space travel, illustrating that the ultimate limits of human exploration are as much philosophical as they are physical. Ensuring a balance between survival, well-being, and freedom requires careful thought, reflecting the ethical dimension of venturing into the cosmos. Even the passage of time itself becomes a tangible factor. Generations may pass without witnessing a destination or receiving updates from Earth. Cultural evolution, changes in social priorities, and adaptations to life aboard the ship will transform the community in ways that are unpredictable. The mission is not static. It is a dynamic system, evolving over decades and centuries, shaped by human behavior, environmental constraints, and unforeseen circumstances. Planning for such evolution requires flexibility, resilience, and anticipation of outcomes that may diverge from initial assumptions. Human space travel across generations is therefore an exercise in patience, foresight, and humility, recognizing that time itself is both companion and constraint. Technological maintenance is another continuous requirement. Systems that function flawlessly today may degrade over decades or centuries. Replacement parts, repair skills, and the capacity to innovate within the limited resources of a spacecraft are essential. Autonomy becomes critical, as real-time support from Earth is impossible. Generational crews must inherit not only the hardware but also the knowledge, judgment, and expertise required to maintain it. Education, documentation, and culture all become part of the infrastructure that sustains life, demonstrating that technology alone is insufficient without human adaptability. Energy management remains central. Power sources must be reliable over centuries, whether nuclear, solar, or other advanced technologies. Energy must be allocated for propulsion, life support, lighting, agriculture, and daily activities, and redundancy is necessary to prevent catastrophic failure. Every system is interdependent, and every miscalculation can propagate, affecting multiple aspects of life and survival. The weight of energy constraints reinforces the broader lesson that human limits, technology, and environment are inseparable in planning interstellar journeys. Even with careful planning, the unknown remains. Cosmic events, unanticipated hazards, and gradual wear and tear can create unforeseen challenges. Generational crews must be capable of responding adaptively, balancing immediate needs with long-term sustainability. Contingency planning, flexibility, and resilience are therefore embedded into both the culture and technical systems of the vessel. Human exploration on this scale is a continuous negotiation with uncertainty, demanding not only preparation but adaptability across lifetimes. Finally, the generational model illustrates the profound commitment required for truly long-distance human space travel. It is a vision that extends beyond a single human lifespan, where the ambitions of one generation are carried forward by their descendants, sustained by careful planning, robust systems, and enduring cultural practices. This approach underscores the limits of individual human achievement and the necessity of collective, long-term thinking when contemplating voyages that may span centuries. Generations among the stars are therefore a testament to both the challenges and the remarkable potential of human ingenuity, patience, and adaptation in the face of cosmic scale. Envisioning travel to distant stars brings with it an inevitable question. How can humans endure the vast stretches of time required to traverse such unimaginable distances? Even with generations of life aboard a spacecraft, the span of human lifetimes remains a limiting factor. This is where the concept of cryosleep, or suspended animation, enters the conversation, offering a method of preservation that could allow individuals to survive long-duration voyages without the continuous wear of biological processes. Cryosleep is not just a technical challenge, it is a profound intersection of biology, engineering and imagination, a means to extend the reach of human presence into regions where the slow accumulation of years would otherwise be prohibitive. The concept of cryosleep relies on slowing the body's metabolism to a near halt, dramatically reducing energy consumption, nutrient requirements, and biological degradation. On Earth, this process is inspired by natural phenomena, such as hibernation in bears or torpor in certain small mammals, where metabolic activity is suppressed to conserve energy during times of scarcity. Translating these natural strategies into human technology requires a delicate balance of chemistry, temperature, and support systems. Even small deviations can produce catastrophic effects, highlighting that suspended animation is not merely a pause, but a complex state that must maintain life without producing damage over extended periods. Early experiments focus on understanding how cells, tissues, and organs respond to extreme reductions in temperature and metabolic activity. Cryoprotectants, chemical agents that prevent ice formation and cellular damage, are essential, but their toxicity and long-term effects must be carefully controlled. Techniques must ensure that, upon revival, the body can resume normal function without cumulative damage to organs, neurological systems, or cellular integrity. These challenges make the application of cryosleep to humans a problem not only of technology, but of physiology, requiring interdisciplinary knowledge spanning biochemistry, engineering, and medicine. The engineering of a cryosleep chamber is equally crucial. These systems must maintain precise temperatures, monitor metabolic indicators, and provide life-sustaining support even as the occupant's body is largely inactive. Oxygen, carbon dioxide removal, waste management, and temperature regulation must continue to function autonomously for extended periods. Any failure in these systems could compromise the viability of the occupant, underscoring that cryosleep is as much about reliability and redundancy as it is about biological preservation. In effect, each chamber is a miniature life support system designed to function indefinitely, with careful calibration and continuous monitoring, ensuring safety across durations that may extend decades or even centuries. The psychological dimension, though subtle, is also significant. Humans are not naturally adapted to being unconscious for long periods, and there may be unforeseen neurological or cognitive consequences from prolonged stasis. Even the process of entering and emerging from suspended animation requires careful consideration of sensory input, orientation, and adaptation to the environment. Cryosleep, therefore, is more than a passive state. It is a carefully engineered transition, orchestrated to maintain both physical and mental integrity. Designing for these transitions is a critical aspect of ensuring that individuals can participate meaningfully in missions once revival occurs. Energy efficiency is another compelling advantage of cryosleep. By dramatically reducing metabolic needs, the resources required to sustain life, food, water, and oxygen, are minimized, reducing the total mass and energy required for long-duration travel. This has profound implications for mission design, allowing spacecraft to carry more scientific equipment, shielding, or other critical systems rather than excessive consumables. Cryosleep shifts the constraints of human limits from continuous life support to periodic support, effectively stretching the capacity of technology to maintain life over the vast scales required for interstellar travel. The implementation of cryosleep also intersects with social and ethical considerations. Decisions about who undergoes suspended animation, how long they remain in that state, and how successive generations are managed must be addressed. In multi-generational or long-duration voyages, cryosleep may be used to stagger populations, reduce resource strain, or align travel with mission milestones. Each decision carries implications for social dynamics, cultural continuity, and the psychological well-being of both those in stasis and those who remain awake. Human space travel in this context becomes as much a social engineering problem as a technical one, requiring careful planning across dimensions that extend far beyond propulsion and life support. Even within theoretical applications, the concept raises questions about perception of time. For those in cryosleep, the subjective passage of time is dramatically reduced, essentially pausing personal experience while decades or centuries unfold outside. This introduces unique challenges in communication, integration with awake crew members, and continuity of personal identity. Managing these aspects is as important as maintaining physical health, illustrating that the human experience of space travel is deeply affected by the mechanisms employed to traverse it. Suspended dreams in this sense extend the limits of endurance while introducing entirely new domains of human adaptation. Cryosleep also influences the design of habitats and spacecraft. Chambers must be integrated with energy systems, waste management, oxygen regulation, and environmental monitoring, ensuring that occupants are maintained safely even when inactive. The arrangement of these systems affects ship layout, mass distribution, and the overall architecture of the vessel. In essence, the implementation of suspended animation drives decisions that cascade across engineering, planning, and habitability, demonstrating the interconnectedness of technology, biology, and mission design in extreme space travel scenarios. Scientific experiments on Earth and in orbit provide incremental insight. Short-term hypothermic states, metabolic suppression in cells and tissues, and pilot studies in microgravity all contribute to the understanding necessary to eventually implement cryosleep on humans. These experiments reveal subtle effects on cardiovascular function, neural activity, and metabolic pathways, highlighting the delicate balance required to maintain life during long periods of inactivity. Each step in research not only advances technical feasibility, but also informs protocols for monitoring, revival, and integration of individuals into active mission roles. The potential applications of cryosleep extend beyond individual survival. For missions spanning decades to reach exoplanets, suspended animation allows synchronization of crew activity with mission milestones, reduces resource demands, and allows gradual acclimation to life on new worlds. It offers a bridge between the slow pace imposed by vast distances and the practical limitations of human lifespans, effectively compressing subjective experience while maintaining continuity of mission objectives. In this sense, cryosleep is both a technical solution and a conceptual framework, redefining how humans might experience and endure extended exploration of space. Even speculative implementations must consider emergency scenarios. Automated monitoring, backup life support, and revival protocols must be robust, ensuring that occupants are maintained even in the event of power fluctuations, system degradation, or unforeseen environmental changes. Every detail, from temperature control to oxygen flow, must be designed for long-term reliability, reflecting the interplay between engineering foresight and biological necessity. Suspended animation is therefore both a dream and a precise technical challenge, requiring integration of multiple disciplines and a commitment to redundancy and resilience. Social and ethical considerations remain profound. The individuals placed into cryosleep may not witness the full arc of the mission, or participate in decision-making. Their dependence on automated systems and awake crew members raises questions about autonomy, consent, and responsibility. Planning for long-duration voyages that incorporate suspended animation must address these dimensions, ensuring that ethical frameworks are integrated alongside technical solutions. The human dimension of space travel is inseparable from the technical, and the implementation of cryosleep exemplifies this integration. Energy efficiency, again, is a key benefit. By reducing metabolic activity, cryosleep minimizes the consumption of resources necessary for survival, freeing energy for propulsion, environmental control, or scientific instrumentation. The cumulative savings over decades of transit are significant, making long-duration missions more feasible. Suspended dreams allow humans to extend presence into regions of space that would otherwise be inaccessible, balancing the limits of biology with the vast scales of the cosmos. Each kilowatt conserved, each gram of food preserved, becomes part of the calculus that defines the practical limits of exploration. Even from a psychological perspective, cryosleep allows the human mind to experience time differently. Subjective experience is compressed, while the universe unfolds externally. This raises unique questions about memory, identity, and adaptation. Individuals awaken into a world that has progressed decades or centuries beyond their own experience, requiring careful social, cultural, and operational integration. The suspended dream state is therefore not only a technical solution, but a profound consideration of human cognition and social continuity, demonstrating the breadth of challenges faced when extending life beyond the familiar rhythms of Earth. Cryosleep represents a convergence of technology, biology, psychology, and ambition. It is a method for transcending the temporal limitations of human existence, allowing exploration of regions where ordinary lifespans are insufficient. Each chamber, each protocol, and each simulation contributes to a broader understanding of how humans might endure long-duration travel, reflecting both the fragility and resilience of life. Suspended dreams offer a pathway to bridge the incomprehensible distances of the cosmos, while maintaining the continuity, health, and identity of the human occupants. Even as humans imagine travelling across vast distances and surviving long-duration voyages, the subtle yet persistent influence of gravity remains a defining factor. Unlike other challenges, gravity cannot be switched off or fully mitigated. It is a constant presence, shaping motion, physiology, and perception in ways that are both immediate and profound. On Earth, we rarely notice its effects, yet every step, every heartbeat, and even the flow of blood through our bodies is tuned to the pull of a planet. Once humans leave this environment, the absence, reduction, or alteration of gravity produces effects that are quietly transformative, demanding adaptation in both body and mind. Microgravity, experienced in low Earth orbit, is one of the most immediate manifestations of this change. Without the familiar pull of a planet beneath them, astronauts experience fluid shifts toward the head, muscle atrophy, and bone density loss. The cardiovascular system adjusts in surprising ways, sometimes producing faint dizziness or other physiological disruptions. Even the senses, finely calibrated to perceive orientation and motion under gravity, must recalibrate. Simple tasks, such as handling tools, moving through narrow corridors, or consuming food, require training, awareness, and subtle adjustments. Gravity's gentle grip is replaced by the inertia of motion, where even small gestures propagate, pushing astronauts through their surroundings with unexpected force. The longer humans remain in microgravity, the more pronounced the effects become. Muscle loss, particularly in the legs and back, necessitates rigorous exercise regimens to maintain functionality. Bones lose calcium, increasing fragility and susceptibility to injury. The vestibular system, responsible for balance and orientation, adjusts to the absence of a gravitational reference, often producing temporary disorientation upon return to Earth. Each adaptation reveals that gravity is not merely a background force, but a shaping principle of human physiology. The body is an ecosystem tuned to a specific gravitational constant, and removing it necessitates ongoing intervention to maintain equilibrium. Partial gravity, such as that on the Moon or Mars, introduces additional complexity. At roughly 1/6 of Earth's gravity on the Moon and 1/3 on Mars, humans must adjust movement, balance, and even cardiovascular function to function optimally. Reduced gravity alters the mechanics of walking and running, increases jump height, and changes energy expenditure in predictable yet subtly challenging ways. Muscles and bones are engaged differently, requiring training and adaptation to prevent long-term degradation. These environments are simultaneously more forgiving than microgravity, yet more demanding than Earth, offering both opportunities and constraints for human activity. Gravity also interacts with human perception and coordination. Motion under reduced or absent gravity produces unique effects on proprioception, the sense of the body's position in space. Objects behave differently, floats may drift, and even simple tasks like pouring liquids or handling delicate instruments require careful attention. The brain must learn to recalibrate motor patterns and expectations, a process that is gradual and continuous. Astronauts describe a shift in awareness, where the familiar cues of orientation and effort must be replaced with new reference points, often relying on visual cues rather than tactile feedback from the environment. Exercise becomes not just a routine, but a critical element of life support in altered gravity. On the International Space Station, astronauts spend hours each day using resistive devices, treadmills and stationary bicycles to counteract the physiological effects of microgravity. These efforts are essential to prevent muscle atrophy, maintain cardiovascular function, and preserve bone integrity. In environments with partial gravity, similar regimens are required, albeit adjusted to the specific gravitational constant. Maintaining physical conditioning is a continuous process, requiring discipline, monitoring, and the careful integration of technology and human effort. Long-duration missions amplify these challenges. As humans travel to Mars or beyond, the cumulative effects of altered gravity over months or years become significant. Physiological adaptation must be complemented by habitat design that accommodates both movement and exercise, ensuring that humans can perform essential tasks without compromising health. Even minor oversights in activity levels, nutrition, or mechanical support can accumulate, producing lasting effects on the body and complicating mission objectives. Gravity is therefore not merely an environmental factor, it is a governing principle that shapes every aspect of human travel beyond Earth. Gravity's influence extends to the mechanics of spacecraft and mission design. Acceleration, deceleration, and maneuvering must account for the mass and inertia of both the vessel and its occupants. Microgravity affects not only human physiology, but also fluid dynamics, combustion, and the behavior of materials. Every engineering system interacts with the absence or reduction of gravity, producing both predictable and subtle challenges. Designers must consider these interactions in every component, from plumbing and air circulation to scientific instruments and propulsion systems. The gentle pull of gravity, or its absence, reverberates through the entire architecture of space travel. Even psychological effects emerge from altered gravity. Humans are accustomed to walking, running, and interacting with their environment under the constant pull of a planet. Removing this reference can produce feelings of disorientation, altered spatial awareness, and subtle stress. Cognitive performance can be affected, requiring careful design of a living and working spaces to support orientation, comfort, and productivity. Gravity is thus intertwined with mental as well as physical well-being, illustrating that human limits in space are defined not solely by distance or propulsion, but by the fundamental conditions under which bodies and minds operate. Partial gravity environments also introduce opportunities for adaptation. Lunar or Martian gravity allows training for future long-duration missions, offering a balance between Earth normal forces and the absence of full gravity. Astronauts can experiment with mobility strategies, habitat layouts, and resource utilization in conditions that approximate otherworldly environments. These experiences provide insight into long-term adaptation, informing mission planning for more distant voyages. Gravity is simultaneously a challenge and a tool for preparation, shaping both engineering design and human readiness. Even minor variations in gravitational force have cascading consequences. For example, fluid management in microgravity requires careful control of pumps, valves, and containment systems, while reduced gravity affects thermal convection, air circulation, and particulate behavior. Dust, liquids, and gases behave differently, requiring continuous monitoring and adjustment. Human activity must be adapted to these conditions, as even simple tasks can produce unintended effects. The interplay between gravity, environment, and human action is continuous and dynamic, emphasizing the complexity of survival and functionality beyond Earth. Education and training for altered gravity are essential components of long-duration missions. Astronauts practice movement in simulated environments, such as parabolic flights or neutral buoyancy pools, to develop motor skills, coordination, and confidence. These exercises are not merely academic, they are preparation for the subtle, continuous adjustments required to operate effectively in space. The learning process is ongoing as humans encounter new gravitational contexts, and it highlights the adaptability of the body and mind when guided by careful preparation and experience. Gravity also interacts with long-term habitation strategies. Rotational habitats, designed to simulate artificial gravity through centripetal force, offer potential solutions for extended voyages. These systems require precise calculations of rotation speed, radius, and structural integrity to provide consistent gravitational effects. They also introduce unique engineering challenges, such as Coriolis effects, which can affect perception, balance, and movement. Even in hypothetical designs, the influence of gravity shapes architecture, energy allocation, and human activity, demonstrating that it is a central factor in planning for survival and functionality in space. The subtle but persistent effects of gravity extend to biology at the cellular level. Microgravity can influence gene expression, immune function, and cellular repair processes. Long-term exposure may have cumulative effects that are not yet fully understood, emphasizing the importance of monitoring, research, and careful adaptation. Gravity is therefore not merely a mechanical force, it is a foundational principle influencing life at every scale, from whole-body coordination to molecular processes. Understanding and mitigating its absence is essential for extending human presence beyond Earth. Even cultural and social aspects are shaped by gravity. Human movement, recreation, and interaction are grounded in expectations formed on Earth. Altered gravity changes how people engage with space, interact with one another, and perceive their environment. Habitats, furniture, and daily routines must be designed to accommodate these differences, ensuring both functionality and comfort. Gravity, in this sense, is intertwined with the lived experience of space travel, influencing behavior, social dynamics, and the psychological framework within which humans operate. Gravity is a lens through which the limits of human endurance and ingenuity can be appreciated. The body, mind, and technology must all adjust to conditions fundamentally different from those in which life evolved. Every system, from life support to propulsion to social organization, must account for the absence or alteration of the familiar pull of a planet. Human exploration is therefore defined not only by distance, energy, or speed, but by the capacity to understand, adapt to, and thrive under the subtle constraints of gravity. It is a gentle, persistent force, invisible yet profoundly influential, shaping every step, every breath, and every choice in the vastness beyond Earth. Space is not empty in the sense of being benign. It is a medium filled with subtle, often invisible forces that challenge the survival of humans beyond Earth. Among the most pervasive of these is cosmic radiation, a stream of high-energy particles that permeates the solar system and beyond, originating from the Sun, distant stars, and events of immense scale such as supernovae. These particles travel at speeds approaching the speed of light, invisible to the naked eye yet carrying enough energy to ionize atoms, damage DNA, and interfere with electronics. While the vacuum of space might appear calm, it is alive with motion and energy, a dynamic environment that tests every aspect of human endurance, engineering, and adaptability. Even within the relatively protected environment of low Earth orbit, radiation is a constant presence. Earth's magnetic field and atmosphere provide shielding, deflecting many high-energy particles and protecting the surface from most solar and cosmic radiation. Astronauts aboard the International Space Station still receive higher doses than those experienced on the planet, and careful monitoring, shielding, and mission planning are essential to manage exposure. As missions extend beyond this protective cocoon, such as to the Moon, Mars, or deep space, these invisible hazards grow in intensity and importance, shaping every aspect of spacecraft design, life support, and operational planning. Solar particle events represent one of the most immediate radiation hazards. When the Sun erupts with flares or coronal mass ejections, it releases a torrent of protons and other energetic particles. These sudden bursts can dramatically increase exposure, creating risk for both humans and sensitive electronics. Shielding, storm shelters, and rapid detection systems become essential in mitigating the effects of such events. Crew members may need to retreat to heavily shielded areas within a spacecraft, where every kilogram of material provides a critical barrier. The invisible nature of this hazard requires preparation, vigilance, and constant monitoring, demonstrating that human survival in space depends as much on awareness and response as on engineering alone. Galactic cosmic rays present a different challenge. These particles, originating from outside the solar system, are high-energy atomic nuclei travelling at near-light speeds. Their penetration capacity makes them difficult to shield against, and prolonged exposure poses long-term health risks, including increased cancer probability, cardiovascular damage, and effects on the central nervous system. Unlike solar events, galactic cosmic rays are constant, creating a persistent background risk that accumulates over time. Human missions must therefore incorporate shielding strategies, structural design considerations, and operational planning to minimize cumulative exposure. These invisible forces are a reminder that even in the absence of immediate danger, space remains an environment that is fundamentally hostile to unprotected life. The effects of radiation are not limited to health alone. Electronic systems, which form the backbone of spacecraft operation, are also vulnerable. High-energy particles can induce single-event upsets, damaging microprocessors, disrupting communication, or causing sensor errors. Redundancy, shielding, and fault-tolerant design are therefore essential to ensure operational integrity. Even minor malfunctions can cascade, particularly on long-duration missions where repair or resupply is impossible. Cosmic radiation, though invisible and silent, exerts a constant influence on mission planning, reminding us that both humans and machines are interdependent in the effort to survive and explore. Radiation exposure is cumulative, meaning that even small doses accrued over extended periods can have significant consequences. For missions lasting months or years, managing this cumulative exposure becomes central to life support, mission design, and crew health. Shielding must balance protection with weight constraints, and operational protocols must optimize time spent in exposed areas. Every system, from sleeping quarters to laboratories, is designed with these considerations in mind. highlighting the pervasive influence of these invisible hazards. The challenge is to integrate biology, engineering, and mission planning into a coherent strategy that mitigates risk while enabling meaningful exploration. Protective strategies also extend to habitat design. Water, specialized materials, and structural shielding can reduce radiation exposure, and careful placement of crew quarters, work areas, and storage can optimize safety. Even the arrangement of equipment and corridors can influence accumulated dose, creating a three-dimensional strategy for mitigation. The invisible nature of the hazard requires that planning account for both human activity and environmental factors, with simulations, modelling, and careful measurement guiding design. Life in space is therefore a negotiation with forces that are unseen but no less real than gravity, energy, or propulsion. Psychological effects are also influenced by awareness of radiation risk. Crew members must contend not only with the physical consequences, but with the knowledge that exposure is ongoing and unavoidable to some degree. Maintaining mental well-being requires trust in systems, careful communication, and strategies that balance awareness with reassurance. Education about risk, training in mitigation, and the integration of safety protocols into daily routines help create a sense of control, even in an environment where uncertainty is constant. Cosmic radiation is thus both a physical and cognitive factor, influencing how humans interact with space over extended durations. Long-duration travel outside the protective envelope of Earth highlights the persistent tension between ambition and vulnerability. Missions to Mars, for instance, must account for months of continuous exposure, necessitating careful planning of trajectory, timing, and operational schedule to minimize risk during solar events. For journeys beyond the solar system, where travel may span decades, the accumulation of radiation becomes one of the defining limits of human survival. Every step in mission design must integrate protection, monitoring, and contingency planning, emphasizing that human space travel is as much a matter of risk management as propulsion or resource allocation. Radiation hazards also provide insight into the limits of current technology. Even with advanced shielding, long-term protection against high-energy cosmic rays remains challenging. Material science, engineering design, and emission planning must continue to evolve, exploring new techniques such as electromagnetic shielding, water-based barriers, and innovative habitat layouts. Each solution carries trade-offs in mass, energy, and complexity, reinforcing the principle that exploration is always a negotiation with constraints that are fundamental, persistent, and invisible. Education and preparation for cosmic radiation are critical for both crew and mission planners. Astronauts must understand the effects, the mitigation strategies, and the operational protocols that allow for safe activity during exposure. Sensors, warning systems, and simulations provide data that inform decisions, creating a framework in which invisible hazards can be managed proactively rather than reactively. Even as technology evolves, the principles of monitoring, redundancy, and precaution remain central, demonstrating that human space travel is not merely about overcoming distance, but also about navigating the invisible and persistent challenges that pervade the cosmos. The interaction of radiation with other environmental factors also shapes mission design. Microgravity, thermal control, and life support systems must all account for cumulative exposure, ensuring that both humans and technology can function over extended periods. The invisible nature of these hazards demands constant vigilance, careful calibration, and an understanding of the subtle interactions that influence health, performance, and mission success. Radiation is therefore a silent, continuous presence, guiding every decision, every design choice, and every operational protocol. Even speculative technologies for deep space travel must consider these hazards. Generational ships, cryosleep chambers, and extended voyages to distant stars all require integration of radiation mitigation strategies, Energy allocation, habitat design, and operational scheduling are intertwined with the persistent need to shield humans from these high-energy particles. The invisible hazard shapes not only the technical aspects of the journey, but also the human experience of life beyond Earth, influencing daily activity, social interaction, and the perception of risk. Cosmic radiation also interacts with human limits in subtle ways. Immune function, cellular repair, and cognitive performance are all affected over prolonged exposure. These physiological constraints inform mission duration, crew rotation, and medical protocols. Even with shielding and careful planning, humans are limited by the cumulative effects of exposure, emphasizing that the universe itself imposes boundaries that are inescapable and persistent. The challenge of survival in space is therefore a negotiation between human resilience and the invisible forces that pervade the environment, highlighting both the fragility and adaptability of life beyond Earth. The lessons learned from current missions inform strategies for future exploration. Monitoring, modeling, and measuring radiation exposure provide data that allow incremental improvement in shielding, operational planning, and life support design. Each spacecraft, each orbit, and each experiment contributes to a growing understanding of how to navigate the invisible hazards that define space beyond Earth's protective atmosphere. This accumulation of knowledge is critical for extending human presence into more distant, higher-risk environments. Cosmic radiation and invisible hazards serve as a reminder that space is not a neutral medium. It is dynamic, energetic, and indifferent to human needs. Every mission, whether brief orbital flights or multi-decadal interstellar journeys, must contend with these persistent influences. The invisible forces shape mission design, operational planning, human physiology, and psychological well-being, forming a continuous backdrop against which the ambition of exploration must be measured. Awareness, preparation, and adaptation become as essential as propulsion, energy management, and life support. These forces are a quiet but constant companion on every journey, defining the limits and the possibilities of human presence beyond Earth. Travelling at velocities approaching the speed of light introduces effects that are far from intuitive, reshaping not only distance and energy considerations, but the very experience of time itself. The universe is not indifferent to motion. It imposes subtle but profound constraints, and Einstein's theory of relativity explains that time is not a universal constant, but a flexible dimension that bends in response to speed and gravity. For humans venturing into deep space, this has profound implications. The aging process, the passage of years, and the synchronization with those left on Earth are all altered in ways that challenge perception and expectation. Relativity transforms time from a familiar, predictable flow into something dynamic, contextual, and inextricably linked to the scale and speed of travel. Even modest fractions of light speed produce measurable effects. As a spacecraft accelerates, time for those aboard begins to diverge from time for those who remain at rest relative to Earth. Minutes, hours, and days stretch differently depending on velocity, and as speeds increase further, the effect becomes more pronounced. This phenomenon, known as time dilation, means that astronauts on extended journeys may experience years while decades or centuries pass elsewhere. The mathematics of this relationship is precise, yet its human implications are extraordinary. Travellers must reconcile their subjective experience with the objective passage of time in the universe, a challenge that touches both psychology and planning. The effects of relativity extend beyond perception to biological aging. In near light-speed travel, the processes that govern cell division, metabolism, and aging are experienced differently for the traveller compared to those remaining behind. While a human might age only a few years on a journey, far more time could elapse on Earth. This divergence complicates communication, coordination, and even social connections, raising unique questions about continuity of experience, relationships, and generational overlap. Time, in this context, is no longer an absolute reference, but a flexible, context-dependent phenomenon that defines both opportunity and limitation in human space travel. Even short-term missions illustrate these principles. While the differences are minute at conventional orbital velocities, they are measurable with precise instruments. Atomic clocks, synchronized before launch, reveal tiny discrepancies after weeks or months in orbit. These small-scale observations provide practical validation of relativity and highlight the subtle ways in which motion influences the flow of time. Scaling these effects up to interstellar travel magnifies them dramatically, transforming the conceptual and operational framework of long-duration missions. The universe does not allow speed to be disentangled from temporal experience. Every acceleration is also a shift in the passage of time. The implications for human planning are profound. Generational voyages, long-term exploration, and even near-light-speed missions require careful accounting of relative time. A crew may depart for a distant star and return to find centuries have passed on Earth, altering cultural, technological, and social landscapes. Maintaining coherence between subjective experience and objective reality becomes an essential part of mission design, influencing choices about communication, documentation, and even societal structures aboard long-duration spacecraft. Relativity is therefore not merely a theoretical concern. It shapes the practical realities of survival, adaptation, and interaction with the wider universe. Navigating relativistic effects also influences propulsion planning. Accelerating to significant fractions of light speed requires immense energy, and the consequences of time dilation must be integrated into trajectory calculations. Decisions about acceleration, deceleration, and velocity profiles are intertwined with biological, psychological, and logistical considerations, illustrating the inseparability of physics and human experience. Every maneuver becomes a negotiation between energy expenditure, mission duration, and the temporal realities imposed by the speed of light. The effects are cumulative, and careful planning is required to ensure both mission success and crew well-being. Even communication is shaped by relativity. Signals travelling between a high-velocity spacecraft and Earth are subject to delays and frequency shifts. Messages may take years to arrive, and the timing of information transfer must account for both distance and relative velocity. For deep space missions, this creates challenges in coordination, emergency response, and ongoing management. The universe imposes a rhythm that cannot be altered, and human technology must adapt to operate effectively within it. Time, relativity, and aging are therefore central not only to individual experience, but to the structure and planning of exploration itself. Biological systems are subtly affected by these conditions. Metabolism, cellular repair, and circadian rhythms are all linked to temporal cycles. Travelling at relativistic speeds may not change these processes directly, but the context in which they occur, relative to external time, shifts. Mission planners must account for these divergences to maintain health, schedule activity, and ensure effective operation over extended durations. Time dilation thus influences physiology indirectly, adding complexity to an already intricate challenge of sustaining human life beyond Earth. Even the perception of duration is transformed. A journey that takes a century from the perspective of Earth may feel like a few decades to the crew aboard a near-light-speed vessel. This divergence alters the experience of life, memory, and anticipation. Planning for these temporal differences requires consideration of generational continuity, crew rotation, and the preservation of knowledge. Education, cultural transmission, and psychological support must all adapt to an environment where the subjective and objective flows of time differ, illustrating the depth of influence that relativity exerts on human experience. Hypothetical applications further demonstrate the interplay of time, speed, and aging. A crew travelling to a nearby star at 90% of light speed might experience only a few years of subjective time, while centuries elapse on Earth. This has profound implications for social connection, mission continuity, and historical awareness. Technologies such as cryosleep, autonomous management systems, and long-term societal planning become essential, ensuring that humans can both endure the journey and integrate meaningfully with the universe upon arrival. Relativity thus transforms human space travel from a mechanical challenge into a complex temporal negotiation. Even navigation and trajectory planning must incorporate time dilation. Acceleration and deceleration profiles are influenced by relativistic physics, requiring precise calculations to ensure arrival at the intended destination and proper synchronization with mission objectives. Energy requirements, propulsion strategies, and life support design are all affected by the relativistic passage of time, highlighting the inseparability of physical, biological, and temporal considerations. Every decision in high-velocity travel is intertwined with the flow of time, creating a multi-dimensional challenge that is unique to the cosmos. Communication across relativistic distances introduces unique phenomena as well. Signals experience redshift or blueshift depending on relative velocity, and delays become increasingly significant as speeds approach light. Coordination with mission control, data transfer, and real-time monitoring are all constrained by these factors, requiring autonomy and predictive planning. Humans must adapt not only to the physical challenges of travel, but also to the temporal realities imposed by motion, learning to operate effectively in a framework where past, present, and future are experienced differently depending on context. Even everyday life aboard a spacecraft is affected. Scheduling, routines, and the perception of elapsed time must account for the relative flow of time between crew and mission planners on Earth. Birthdays, anniversaries, and milestones take on new meaning when subjective and objective time diverge. Education, cultural transmission, and psychological support all require adaptation, illustrating that time dilation has consequences far beyond physics, influencing the structure of human society and experience in profound ways. Energy management is further influenced by these temporal considerations. Longer subjective durations for the crew may require sustained life support systems, energy for environmental control and maintenance over periods that, while shorter for the travellers, correspond to extended operational needs. Balancing propulsion, energy allocation, and life support across relativistic timeframes becomes a central aspect of mission design, integrating physics, engineering, and human endurance. Finally, the relativistic effects on aging and perception are a reminder that human exploration is constrained not only by technology and biology, but also by the fundamental structure of the universe. Time is not an absolute measure, but a contextual framework, shaping experience, planning, and expectation. Humans venturing among the stars must navigate not only distance and energy, but the subtle, pervasive influence of relativity itself, integrating knowledge of physics with the realities of life, psychology, and culture. Time, relativity, and aging are thus both limit and guide, defining the framework within which humanity might one day extend its presence into the cosmos. Venturing beyond the solar neighbourhood requires humans to confront scales, distances, and challenges that stretch the imagination and the limits of technology alike. Once we move past the orbit of Neptune and the distant objects of the Kuiper Belt, we enter a region where the Sun is no longer a dominant anchor, where interstellar space begins to assert itself in ways both subtle and profound. The familiar patterns of planets, magnetic fields, and solar winds fade into the cold expanse of near emptiness, and the environment becomes one in which the vastness of the cosmos is experienced not only intellectually, but viscerally. Exploring beyond the solar neighbourhood is not merely a question of propulsion, energy, or life support. It is a confrontation with scale, time, and the relentless sparsity of space. The first consideration is distance. Even the closest stars are separated by light years, which are units so large that conventional metrics lose meaning. Proxima Centauri, the nearest stellar neighbour, lies over 4 light-years away, a span that dwarfs every journey humanity has ever attempted. Travelling to such a star using chemical propulsion would require tens of thousands of years, far exceeding human lifespans. Even advanced propulsion concepts, whether nuclear, ion, or theoretical fusion-based systems, must contend with the enormous energy requirements, the slow accumulation of distance, and the biological and logistical challenges posed by extended transit. Exploring this domain is therefore a study in patience, planning, and the creative application of every tool at humanity's disposal. Energy management becomes exponentially more complex as we move beyond the protective envelope of the sun. Solar radiation diminishes with distance, reducing the efficacy of solar panels and forcing reliance on nuclear or other long-duration energy sources. Life support, communications, and propulsion systems must operate autonomously for decades or even centuries without resupply or repair from Earth. Every resource, from oxygen to food to spare parts, must be carefully calculated, recycled, and preserved. The farther from the sun, the more the challenges of sustaining life and motion intertwine, reinforcing the notion that the void is an environment defined by subtlety, scarcity, and the persistent need for careful orchestration. Communication is another profound challenge. Signals, travelling at the speed of light, take years to reach even the nearest stars. Real-time coordination with Earth becomes impossible, and autonomy becomes a necessity rather than an option. Crew members, or autonomous systems, if humans cannot be transported, must make decisions independently, relying on predictive models, simulations, and contingency protocols. The structure of time, previously predictable and shared across Earth-based systems, now diverges from the subjective experience of travellers. Every action must be planned with foresight, anticipating conditions that cannot be corrected immediately. The solar neighbourhood is no longer a community. It becomes a domain in which isolation is intrinsic, and planning must accommodate both the vastness of space and the persistence of the laws that govern it. The environmental hazards of interstellar space are subtle, yet persistent. Cosmic rays, high-energy particles, and interstellar gas, though sparse, present long-term risks to both human physiology and electronic systems. Shielding becomes both critical and challenging, as additional mass increases the energy required for propulsion. Even minor micrometeoroids travelling at immense speeds pose significant threats to structural integrity. The interplay of risk, protection, and energy management defines the operational framework, requiring redundancy, foresight, and robust systems capable of functioning autonomously for extended periods. Exploration beyond the solar neighbourhood is therefore as much a problem of mitigation and resilience as of distance and speed. Psychological factors also become central to long-duration interstellar exploration. Isolation, monotony, and the absence of familiar reference points can affect mood, cognition, and social dynamics. Generational planning, cryo-sleep, or highly autonomous robotic systems may be required to sustain the continuity of operations. Maintaining morale, cognitive function, and social cohesion becomes as essential as maintaining oxygen, food, and energy. Every system must be designed with both technical precision and human experience in mind, as the faintest disruptions can accumulate over decades or centuries, amplifying small stresses into significant operational challenges. Navigating these distances requires both ingenuity and patience. Gravity assists, careful trajectory planning, and the exploitation of local resources can extend the range and efficiency of spacecraft. Even subtle interactions with interstellar magnetic fields, plasma streams, or micrometeoroid distributions must be accounted for in high-fidelity simulations. Exploration beyond the solar neighbourhood is not a matter of simply pointing a spacecraft toward a distant star. It is a continuous negotiation with a medium that is sparse yet non-trivial, in which every decision has long-term consequences. Autonomy, predictive modelling, and adaptive systems are not luxuries. They are necessities for any meaningful journey into these regions. The question of sustainability becomes increasingly profound. Even with advanced propulsion and life support, the ability to maintain human life over decades or centuries depends on the careful balance of resources, energy, and habitat integrity. Closed-loop systems for food, water, and air must be nearly perfect, as even minor inefficiencies magnify over time. Maintenance, repair, and adaptation must be integrated into both human behavior and automated systems. Exploring beyond the solar neighborhood is therefore a lesson in resourcefulness, patience, and the capacity to anticipate cumulative effects of environmental and operational challenges. Even navigation itself is a challenge. Interstellar distances require precision beyond anything encountered in planetary or even solar system travel. Tiny deviations in trajectory, uncorrected over years, can result in missing a destination entirely. Observations of distant stars, gravitational perturbations from unseen masses, and the motion of the galaxy itself must be considered in planning. Every measurement, calculation, and adjustment is amplified by scale, emphasizing that navigation beyond the solar neighborhood is as much about prediction and foresight as it is about mechanics and propulsion. The concept of speed also takes on new significance. While chemical propulsion is sufficient for planetary or solar system travel, interstellar distances demand velocities approaching significant fractions of light speed. Achieving and maintaining such speeds introduces relativistic effects, energy demands, and navigation complexities. Acceleration must be carefully planned to minimize structural stress on both the vessel and its occupants. Even microvariations in thrust or energy allocation can have long-term consequences. Exploration of this domain is therefore both technical and temporal, integrating physics, engineering, and human endurance in ways that surpass previous experience. Communication, autonomy, and mission architecture are intertwined with the limits of time and speed. Messages may take years to arrive, repairs may be impossible, and decisions must be made independently. Generational planning, suspended animation, or autonomous robotic systems are considered to mitigate the challenges of isolation and temporal delay. Even when humans are involved, careful orchestration is necessary to maintain the continuity of knowledge, social cohesion, and operational integrity. The universe, silent and indifferent, defines these boundaries, emphasizing the need for anticipation, resilience, and careful planning. Even the notion of observation changes. Light from distant stars takes years or centuries to reach the spacecraft, meaning that all visual information represents the past. Scientific instruments, navigation tools, and observational protocols must account for these temporal shifts, interpreting data in context rather than assuming real-time correspondence. The experience of space becomes one in which perception is always delayed, filtered, and shaped by both distance and the finite speed of light. Exploration beyond the solar neighborhood requires an understanding of both physical and perceptual realities, and an acceptance that the universe operates on scales that dwarf human lifespans and intuition. Life, resource management, and social organization are all profoundly affected. Food, water, and energy systems must be closed-loop and highly efficient, while social structures must endure across generations or periods of suspended animation. Education, knowledge transfer, and cultural continuity are critical, ensuring that skills, information, and decision-making capacity are maintained over extended periods. The vessel itself becomes a self-contained society, requiring foresight, planning, and continuous adaptation to the cumulative effects of isolation, time, and the operational challenges of interstellar travel. Even risk assessment evolves in this domain. Micrometeoroid collisions, exposure to cosmic radiation, and failures in critical systems take on heightened significance when opportunities for repair or resupply are non-existent. Mitigation strategies must be comprehensive, accounting for both predictable and stochastic hazards. Redundancy, modularity, and adaptability become central principles, as does the cultivation of a culture in which both humans and machines are prepared for contingencies that may unfold over years or decades. Exploration beyond the solar neighbourhood is therefore a continuous exercise in anticipation, resilience, and thoughtful planning. The boundaries of human endurance are also redefined. Lifespans, metabolic rates, and cognitive capacities must be reconciled with travel times, energy budgets, and operational requirements. Techniques such as cryosleep, artificial gravity, and advanced life support are not optional. They are central to the feasibility of long-duration interstellar travel. Human limits, technical constraints, and the vastness of space converge to define a landscape in which ambition, ingenuity, and patience are inseparable from the practical realities of survival and exploration. Exploring beyond the solar neighbourhood is a venture into scale, time, and subtle environmental hazards that extend well beyond prior experience. Every system, every protocol, and every adaptation must be considered in the context of extreme distances, prolonged duration, and the pervasive influence of an environment that is simultaneously empty and alive with subtle forces. Human exploration in this domain demands not only technological innovation, but psychological resilience, social cohesion, and a profound appreciation for the scale of the universe. It is a journey that transforms understanding of distance, time, and human limits, revealing both the fragility and the remarkable adaptability of life in the vast reaches beyond the sun. Human curiosity has a tendency to stretch beyond what is immediately possible, reaching into the realms of imagination, theory, and speculative physics. When considering travel across light years of empty space, the limitations of conventional propulsion seem almost overwhelming. This is where concepts like wormholes, warp drives, and other exotic forms of faster-than-light travel enter the discussion. While entirely theoretical for now, these ideas illustrate how physics, creativity, and ambition intersect, offering glimpses of what might one day transform our understanding of motion, distance, and human presence in the cosmos. Even in imagining what cannot yet be realized, humans engage in a subtle form of exploration, one that extends the boundaries of possibility while remaining grounded in the laws of the universe. Wormholes, for instance, represent a hypothetical shortcut through the fabric of space-time. If such structures exist, they could allow a traveller to move between two distant points almost instantaneously, bypassing the vast distances that would otherwise require decades or centuries of transit. The mathematics of general relativity permits these solutions under certain conditions, yet the practical construction, stabilization, and traversal of a wormhole remain firmly in the realm of speculation. Exotic matter, negative energy, and untested physical principles would be required to keep a wormhole open and safe for passage. Even without practical implementation, the concept serves as a framework for thinking about the universe in new ways, emphasizing the interplay between physics, imagination, and the limits imposed by nature. Warp drives offer a similarly speculative but fascinating approach. Unlike conventional propulsion, which moves a spacecraft through space, a warp drive conceptually contracts space in front of a vessel and expands it behind, allowing effective faster-than-light travel without locally exceeding the speed of light. Proposed models, such as the Alcubierre drive, require immense energy densities and exotic forms of matter far beyond current technological capability. Yet these models provide insight into the fundamental principles that govern space-time, suggesting that even seemingly impossible journeys might be constrained less by imagination than by the resources and understanding required to manipulate the universe at its deepest level. Such speculative physics expands the conceptual horizon, allowing humans to explore what is theoretically permissible, even if practically unreachable. Even the discussion of these concepts requires a delicate balance between creativity and scientific rigour. Wormholes and warp drives are not science fiction in the casual sense. They're grounded in the mathematics of general relativity and the known structure of space-time. The challenge lies in translating these elegant equations into practical mechanisms. Energy requirements, stability concerns, causality and radiation effects all introduce constraints that are subtle, technical, and profoundly significant. These obstacles highlight the difference between what is theoretically permissible and what is physically achievable, reminding us that the universe imposes rules even on imagination. The concept of faster-than-light travel also reshapes our understanding of time. If a spacecraft could traverse vast distances almost instantaneously via a wormhole or warp bubble, the subjective experience of time aboard the vessel might differ dramatically from the passage of time in the rest of the universe. The relativistic effects that dominate conventional near-light speed travel would be circumvented in theory, offering a radically different approach to aging, communication, and synchronization. Even the speculative nature of these concepts illustrates how closely time, space, and human experience are intertwined when imagining interstellar travel. While the practical implementation of these technologies is currently beyond reach, considering them shapes our approach to problem-solving in space travel. Thinking about how to manipulate space-time encourages creative engineering, inspires alternative propulsion concepts, and motivates research into high-energy physics, quantum mechanics, and the properties of exotic matter. The pursuit of what is impossible in the present lays the groundwork for discoveries that may redefine the limits of the future. Even unsuccessful experiments, or thought experiments that remain purely theoretical, extend our understanding of the universe and inform the incremental steps that bring practical exploration closer to reality. Exploration in this context also raises philosophical and conceptual questions. If wormholes or warp drives were possible, what would it mean for human experience, perception, and society? How would the ability to traverse light years in moments reshape civilization, communication, and culture? These questions are speculative, yet they encourage reflection on the interplay between physics, ambition, and the human desire to transcend limitation. Considering these possibilities invites a kind of intellectual travel, where the journey occurs not through distance, but through ideas, models, and imaginative reasoning, offering insight into the nature of the universe and our place within it. Even within our current understanding, these speculative concepts illuminate the constraints of conventional travel. The sheer distances between stars, the limits imposed by the speed of light, and the energy requirements for high-velocity propulsion make interstellar journeys daunting. Wormholes and warp drives serve as conceptual counterpoints, illustrating what might be achievable if fundamental barriers could be negotiated. They encourage scientists and engineers to explore edge cases, think beyond standard approaches, and investigate materials, energy sources, and physical interactions in ways that extend our understanding of feasibility. The very act of considering the impossible refines our grasp of the possible. The pursuit of speculative physics also influences mission planning indirectly. Even if practical wormholes or warp drives remain unreachable, understanding their theoretical requirements informs conventional propulsion. Concepts such as energy efficiency, gravitational manipulation, and the management of extreme forces translate into incremental improvements in rocket design, energy storage, and trajectory optimization. Speculation in this sense catalyzes practical innovation, providing inspiration and direction for technologies that can be implemented today or in the near future. Human exploration of space, therefore, progresses through a combination of imagination, theoretical rigor, and incremental engineering. The human imagination thrives in this space between known physics and speculative possibility. Even without the ability to build a warp drive, the very act of modelling such a system encourages interdisciplinary research, deepens understanding of relativity, and inspires generations of scientists, engineers, and explorers. The boundary between theory and application becomes a creative space, where ideas are tested against the constraints of the universe and where failure informs success. Speculative physics, therefore, is not idle dreaming. It is an essential part of the cognitive and cultural framework that drives human expansion into space. Even safety and ethics are shaped by these speculative ideas. Traversing vast distances via exotic means raises questions about causality, resource allocation, and unintended consequences. How would travel through a wormhole affect the surrounding environment? Could manipulating space-time create hazards beyond our immediate perception? These considerations highlight that even in thought experiments, humans must integrate responsibility, foresight, and caution. Speculative physics is therefore a laboratory, not only for technology, but for ethics, judgment, and long-term planning. Each new concept, each theoretical paper, and each model contributes to a gradual expansion of possibility. As research progresses, previously speculative ideas become more constrained by empirical evidence, material science, and energy considerations, while retaining their power to inspire exploration. The universe provides both limits and guidance. While the equations allow certain solutions, the practicalities of energy, materials, and biology shape what could ever be realized. Humans operate within this balance, pushing outward at the intersection of imagination and feasibility, discovering new ways to extend presence, knowledge, and experience. Even contemplation of these concepts has practical value. It encourages the development of new propulsion techniques, materials capable of withstanding extreme energy densities, and computational models that predict and optimize long-duration journeys. Speculative physics informs incremental progress in unexpected ways, driving research into ion drives, nuclear propulsion, and energy-efficient trajectories. Wormholes and warp drives, while not achievable today, catalyze thinking that improves the practicality of near-term missions and inspires innovations that might otherwise be overlooked. In this way, speculation and imagination are partners with observation, experiment and engineering in the ongoing expansion of human reach. Wormholes, warp drives, and other speculative physics concepts remind us that human ambition is not limited by current capability alone. Even within the strictures of known laws, the universe invites exploration of possibilities, both practical and theoretical. They illuminate the boundaries of our understanding, challenge us to reconcile imagination with physics, and provide a vision of what might one day be attainable. The interplay between the impossible and the achievable defines the frontier of human space travel, encouraging patience, curiosity, and sustained inquiry across the scales of distance, energy, and time. Every journey beyond the familiar confines of our solar system is a negotiation with reality, a careful accounting of what must be expended to achieve even the smallest forward motion. Energy and matter are the currencies of space travel, immutable resources that dictate the limits of distance, speed, and duration. Unlike on Earth, where abundant energy flows and consumable materials are often taken for granted, the cosmos is indifferent, offering no resupply and no forgiveness. Every gram of fuel, every joule of energy, every bit of material that leaves a planetary surface carries with it a weight far beyond the literal mass. It represents planning, constraint, and the ultimate cost of venturing into the void. The fundamental principle is deceptively simple. Moving mass through space requires energy. Newton's laws dictate that acceleration, deceleration, and trajectory adjustments all consume measurable amounts of force and, by extension, energy. For a spacecraft carrying humans, life support, instrumentation, and propulsion systems, this accounting becomes complex. Each kilogram added for life support, shielding, or scientific equipment increases the energy required to accelerate the vessel. The relationship is not linear. Additional mass compounds energy requirements, creating a delicate balance in which every decision reverberates across the mission. The ultimate cost of interstellar travel is therefore not a single figure, but a system-wide equilibrium that must be meticulously maintained. Fuel is the first tangible expression of this cost. Traditional chemical rockets provide high thrust but are limited in efficiency, requiring enormous quantities of propellant for even modest velocity increases. For missions beyond the solar system, chemical propulsion is impractical due to the exponential growth of fuel mass with increasing speed. Alternative concepts such as ion drives, nuclear thermal propulsion, or theoretical fusion engines promise higher efficiency but come with their own limitations in energy density, reliability, and feasibility. Each propulsion method embodies a trade-off between mass, energy, and achievable velocity, reminding us that the laws of physics are uncompromising, yet they also guide the design of every viable mission. The interaction between matter and energy extends beyond propulsion. Life support, shielding, and habitat infrastructure all require material mass, which in turn demands energy to transport, maintain, and operate. Water, oxygen, food, and waste recycling systems all represent stored matter, and their presence influences both propulsion planning and mission logistics. Even minor choices in material selection, storage, and utilization cascade into energy requirements, demonstrating that the ultimate cost of travel is holistic, integrating physics, biology, and engineering into a single continuous calculation. Radiation shielding provides a clear example. Protecting humans from cosmic rays, solar particle events, and high-energy radiation demands dense materials, structural design, and energy expenditure for maintenance and monitoring. Each layer of shielding adds mass, which increases energy needs for propulsion, which in turn dictates additional fuel or alternative energy sources. The cost of protection is therefore recursive, a continuous loop in which material and energy are inseparable from the survival of the crew and the success of the mission. The universe enforces these rules silently, with every decision contributing to the cumulative balance of cost and consequence. Energy, in turn, is constrained by generation and storage limits. Solar power, while effective within the inner solar system, diminishes in intensity with distance, necessitating alternative sources for deep space travel. Nuclear reactors provide continuous power, but require careful management, shielding, and heat dissipation. Every watt used for propulsion, life support, or scientific observation subtracts from other operational needs, forcing prioritization and efficiency. The interplay of energy availability, consumption, and distribution shapes the design, scale, and feasibility of long-duration voyages. In this way, energy is not merely a resource but a defining factor that structures the entire mission. Even human biology imposes cost. Every breath, every heartbeat, every metabolic process requires sustenance, oxygen, and waste management. Maintaining life over extended periods compounds the energy and material requirements exponentially. Nutrition, exercise, and medical care all consume stored matter and energy, reinforcing the notion that human survival is inseparable from the physical and logistical architecture of the spacecraft. Each individual is not merely a passenger, but a living system that demands resources and attention, integrating biology into the calculation of ultimate cost. Long-duration interstellar travel magnifies these costs. The farther a vessel travels, the longer it must sustain energy generation, life support, and operational integrity. Even small inefficiencies accumulate, translating into increased energy demands, additional material mass, and heightened planning requirements. Every contingency, every redundancy, and every margin of safety carries a tangible cost in both matter and energy, emphasizing that distance, time, and human survival are interlinked through these fundamental resources. The ultimate cost is not merely calculated in fuel or energy, it is measured in the orchestration of matter, motion, and life over vast expanses. Even speculative propulsion concepts highlight the relationship between energy, matter, and feasibility. Hypothetical fusion engines, antimatter drives, or even conceptual warp systems all rely on manipulating enormous quantities of energy or exotic forms of matter. The magnitude of the required energy dwarfs anything currently achievable, revealing the profound limits imposed by physics. Even as imagination stretches to envision these possibilities, the universe enforces hard boundaries, reminding us that exploration is constrained not only by creativity, but by the immutable relationship between energy, matter, and motion. Resource allocation becomes a constant negotiation. Every gram of consumable material, every joule of energy, and every subsystem integrated into the spacecraft influences the viability of the mission. Decisions about redundancy, shielding, propulsion efficiency, and crew capacity all intertwine in a continuous calculation that balances safety, progress, and sustainability. The ultimate cost is therefore dynamic, influenced by both initial design and operational adaptation over the course of the journey. Even small deviations in planning can have cascading consequences, making precision, foresight, and adaptability essential for success. Beyond the technical aspects, there is also a psychological dimension, understanding that every resource has a tangible cost. Every litre of water, every kilogram of fuel, every watt of energy shapes human behaviour, planning, and decision-making. Crew members must operate with an awareness of scarcity, prioritising tasks, managing consumption, and responding to unexpected situations with both caution and creativity. Human judgment becomes an integral part of the equation, linking physiology, cognition, and material constraints in a continuous feedback loop that defines the mission's success. Even minor inefficiencies in energy or material use are magnified over long durations. Small leaks, minor waste, or slight deviations from optimal energy use can accumulate into significant deficits, jeopardizing both propulsion and life support. Every choice is consequential, emphasizing the integration of technical knowledge, careful monitoring, and adaptive management. In this context, the ultimate cost is experienced not only in abstract calculations, but in daily operations, where the balance between energy, matter, and survival is continuously negotiated. The interplay of energy and matter also influences scalability. Expanding missions to carry larger crews, additional equipment, or more ambitious scientific instruments increases both energy demand and material mass, creating compounding costs. Each extension of capability must be weighed against the exponential growth of resource requirements, illustrating the delicate balance that defines practical limits. Exploration beyond the solar system is therefore not a matter of simply building bigger or faster spacecraft. It is an exercise in efficiency, optimization, and judicious allocation of every available resource. Even theoretical constructs such as multi-generational ships or suspended animation interact with the ultimate cost. Cryosleep reduces the energy and material requirements associated with metabolism, allowing resources to be conserved for long-duration transit. Generational planning distributes consumption over multiple cohorts, yet introduces additional social and logistical complexities. Every innovation that addresses one aspect of the cost introduces secondary considerations, reinforcing the principle that energy, matter, and human limits are inseparable in planning and executing interstellar travel. Risk management is intimately tied to these considerations. Shielding against cosmic radiation, maintaining life support, and ensuring propulsion reliability all demand energy and mass, creating trade-offs that influence mission design. Every redundancy, every contingency plan, and every precautionary measure carries a tangible cost in terms of material and energy, emphasizing that human presence in deep space is always balanced against finite resources. The ultimate cost is therefore both a calculation and a lived experience, shaping how humans interact with space, technology, and one another over extended durations. Energy and matter define the very boundaries of human exploration. The more ambitious the goal, the more exacting the requirements. Moving beyond our solar system requires careful orchestration of resources, precise engineering, and the integration of human needs into every decision. The laws of physics are unyielding, yet they provide a framework within which ingenuity, planning, and adaptation can extend the reach of humanity. Every journey, every calculation, and every system design is a testament to the relationship between energy, matter, and the ultimate cost of venturing into the cosmos. Survival, progress, and achievement are measured not only in distance, but in the meticulous management of the resources that make exploration possible. Stepping beyond the practical considerations of energy, matter, and survival, space travel begins to intersect with thought itself, inviting reflection on the philosophical horizons of human existence. When distances are measured in light years, when time bends under the influence of relativity, and when the cosmos stretches vast and silent in every direction, it is natural to pause and consider what these conditions imply for identity, meaning, and our place in the universe. The human mind, accustomed to terrestrial scales and rhythms, encounters a new kind of vastness, one in which both thought and imagination must stretch to accommodate environments far beyond everyday experience. Philosophical horizons are thus not abstract indulgences. They are integral to understanding how humans might exist, perceive, and act when the familiar reference points of Earth are no longer present. One of the most striking realizations is the fragility and smallness of human life against the backdrop of the universe. The stars, scattered across unimaginable distances, operate on timescales and energies that dwarf human history. A journey to even the nearest star would take decades at speeds approaching the extremes of current technology, and interstellar travel to more distant targets would stretch beyond lifetimes. This juxtaposition of human scale against cosmic scale invites reflection. Our ambitions, achievements, and even struggles exist within a context that is far larger than the mind can easily comprehend. Philosophical horizons arise from this awareness, blending humility with curiosity, grounding aspiration in the reality of scale while inspiring questions that are as old as civilization itself. Isolation becomes another lens through which philosophical reflection is encouraged. In space, humans are separated from the Earth and its familiar ecosystems, landscapes, and societies. The void is indifferent, unchanging, and immense. Every human action, from the simplest maintenance task to complex navigation, occurs within a context that offers no immediate feedback or reassurance from the environment. This isolation magnifies the importance of intentionality, observation, and reflection. Decisions take on philosophical weight. What is worth conserving, pursuing, or risking when the surrounding universe is simultaneously vast and indifferent? Even practical choices such as energy allocation or trajectory adjustments are suffused with significance when survival, experience, and continuity are measured in terms that exceed ordinary human scales. Time also shapes philosophical considerations. Relativity and long-duration travel create experiences in which time passes differently for travellers than for those left behind on Earth. A person might age only a few years on a journey while decades or centuries unfold elsewhere. These divergences introduce questions about identity, generational continuity, and the subjective experience of life. Philosophical horizons emerge from the interplay of personal experience with universal scales, challenging humans to reconcile individuality, legacy, and the broader arc of existence in environments where temporal context is mutable. Questions of connection, memory, and relevance take on new meaning, shaping how humans might conceptualize life, purpose, and societal continuity on interstellar voyages. Ethical considerations naturally arise as well. Planning for multi-generational travel, suspended animation, or long-term robotic exploration requires reflection on responsibility, consent, and the distribution of risk. Decisions made today may affect people born decades or centuries later, shaping their opportunities, safety and well-being without their input. This ethical dimension extends beyond interpersonal responsibility to include the environment of space itself. Cosmic hazards, resource limitations, and technological constraints force careful consideration of how action, inaction, or design choices impact not only the immediate crew, but future generations and even broader human experience. Philosophical reflection is therefore intertwined with technical and operational decision-making, providing a framework for responsible exploration. The interplay between human perception and cosmic scale also informs philosophy. Sensory and cognitive systems evolve for terrestrial conditions, yet space challenges these assumptions. Vast distances, the absence of familiar cues, and altered gravitational environments force humans to perceive and interact with the universe in novel ways. This shift in perspective invites contemplation about the limits of understanding, the role of observation, and the ways in which perception shapes reality. Philosophical horizons emerge from the awareness that humans inhabit a universe simultaneously accessible and incomprehensible, where interpretation, experience, and cognition define both survival and meaning. Existential reflection is further amplified by the awareness of permanence and impermanence. Stars evolve over millions or billions of years, planetary systems form and dissolve, and interstellar environments endure far beyond individual human lifespans. The juxtaposition of ephemeral human existence against cosmic continuity inspires questions about purpose, significance, and legacy. What does it mean to leave a mark in a universe that will persist regardless of individual action? How can humans reconcile ambition with humility, exploration with responsibility, and curiosity with the awareness of transience? These questions are not obstacles to space travel, but essential companions, shaping decision-making, motivation, and the understanding of what it means to exist beyond Earth. Scientific discovery itself has philosophical dimensions. Observing phenomena like cosmic radiation, interstellar medium, gravitational waves, or relativistic effects challenges assumptions about reality and the limits of knowledge. Each measurement, each observation, each calculation contributes to a growing understanding of a universe that is vast, dynamic, and complex. The act of exploring becomes intertwined with reflection. Discovery is both a practical and philosophical engagement in which understanding the cosmos illuminates not only physical truths, but the boundaries and potential of human comprehension. Even social organization and culture are influenced by these horizons. Long-duration travel, whether by generational ships or autonomous systems, requires intentional structures for governance, education, and social cohesion. Philosophical questions about fairness, continuity, and the distribution of resources become tangible operational concerns. Designing societies that function effectively in isolation, over extended periods, and under the constraints of space requires reflection on human nature, ethics, and the principles that allow cooperation to endure. The philosophical horizon thus intersects with both biology and engineering, forming a holistic framework for sustained human presence beyond Earth. Imagination and creativity are also part of these horizons. Considering what might exist in distant star systems, what forms life might take, or how human culture could evolve in isolation, expands cognitive and philosophical frameworks. Speculative thought becomes a tool for preparation, helping humans anticipate, adapt, and innovate in environments that are not fully known. Even theoretical concepts like wormholes, warp drives, or interstellar ecology serve as platforms for philosophical engagement, encouraging reflection on limits, ethics, and the nature of possibility itself. Long-term perspective also shapes motivation. Awareness of cosmic scale, combined with an understanding of energy, matter, and time, informs priorities in mission planning, scientific research, and cultural continuity. Humans must weigh immediate needs against long-term consequences, balancing survival with curiosity, efficiency with exploration, and individual well-being with collective success. Philosophical reflection becomes an active component of operational strategy, integrating knowledge, foresight, and ethical judgment into the practical realities of deep space travel. Even solitude has meaning in these contexts. Extended isolation from Earth and familiar social networks magnifies both psychological and philosophical experience. Reflection, contemplation, and a heightened sense of presence emerge naturally in environments where sensory input is limited and consequences are delayed. Humans may find new perspectives on identity, purpose, and connection when removed from immediate terrestrial context. Philosophical horizons are therefore not abstract musings, but lived experiences that influence decision-making, behaviour, and perception during long-duration voyages. Risk and uncertainty are central to these reflections. The unpredictability of cosmic events, material degradation, and environmental hazards forces consideration of contingency, adaptability, and resilience. Philosophical engagement informs both anticipation and response, shaping how humans interpret uncertainty and make decisions under conditions of extreme isolation and delay. Reflection and planning become inseparable, with the philosophical horizon guiding practical strategies while grounding human experience within the vast scales of space. Contemplating the philosophical horizons of human space travel illuminates both limitation and possibility. Humans exist within a universe defined by vast distances, extreme energies, and the inexorable passage of time. Yet within these constraints, imagination, curiosity, and ingenuity flourish. Ethical, existential, and cognitive considerations are intertwined with operational planning, reflecting a holistic understanding of what it means to extend human presence beyond the familiar. Exploration is therefore as much an engagement with thought, values, and reflection as it is with propulsion, energy, or biology. In imagining the far future of human space travel, it becomes clear that the scale of ambition stretches beyond any single lifetime, past even the limits of generations, into an era where humanity interacts with the cosmos on terms we can barely comprehend. The dreams of this future are both practical and poetic, voyages that span decades, centuries, or millennia, civilizations that move beyond the gravitational anchor of Earth, and technologies that, while unimaginable today, may one day redefine our understanding of distance, time, and survival. These dreams are shaped by current knowledge of physics, biology, and engineering, yet they also demand imagination, foresight, and a willingness to engage with the profound uncertainty inherent in the cosmos. One of the central ideas in contemplating this distant future is the notion of sustainability on an interstellar scale. A spacecraft designed for such travel would need to function not just for years but for lifetimes, supporting ecosystems, human populations, or autonomous systems indefinitely. Closed-loop life support, energy management, and resource recycling would need to reach levels of efficiency and reliability that surpass even our most advanced experimental technologies. Water, oxygen, food, and waste would be continually recycled, and habitats would need to be robust against both the predictable and the unforeseen. The magnitude of planning required is staggering, emphasizing that dreams of the far future are inseparable from the practical realities of survival in a harsh and indifferent environment. Time becomes a central theme in these considerations. Generational ships, cryosleep, and near-light-speed travel all illustrate the ways in which human perception of time diverges from objective passage. Travelers may experience months or years while centuries unfold elsewhere. Synchronization with Earth, continuity of knowledge, and the preservation of culture across such spans all require meticulous planning. Even the act of imagining this future requires stretching thought beyond ordinary human lifespans, engaging with scales of existence that challenge intuition and perception. Dreams of the far future are as much an exercise in temporal imagination as they are in technical or logistical planning. Energy and propulsion remain foundational constraints. Achieving significant fractions of light speed demands enormous energy resources, while sustaining life, communication, and operation over millennia requires continuous power generation. Advanced concepts such as nuclear fusion, antimatter, or hypothetical warp systems illustrate the scale of energy required for truly ambitious interstellar journeys. Every system, from propulsion to habitat life support, must be integrated into a coherent energy framework, emphasizing that human presence beyond the solar system is constrained not only by distance, but by the immutable principles of physics. Dreams of the far future therefore exist at the intersection of possibility and limitation, where imagination must meet fundamental reality. Even the social and cultural dimensions of such travel demand attention. Maintaining cohesion, purpose, and identity over multiple generations or long periods of suspended animation is a challenge both profound and subtle. Education, governance, and knowledge transfer become essential functions, ensuring that subsequent generations can operate effectively, maintain infrastructure, and preserve continuity of mission objectives. Human psychology, behavior, and interpersonal dynamics become as critical as propulsion, shielding, and resource management. The far future is not only a technical question, it is a reflection on human adaptability, culture, and the capacity for long-term planning. Speculative physics continues to play a role in shaping these dreams. Wormholes, warp drives, and other theoretical constructs offer potential pathways to dramatically reduce travel time, though they remain firmly in the domain of mathematics and hypothesis. Considering these possibilities encourages research into fundamental physics, material science, and energy management, while also inspiring imaginative thought about how humans might interact with the universe. Even if these technologies remain unattainable for centuries, they serve as conceptual horizons, motivating both incremental innovation and philosophical reflection about the nature of possibility. Risk and uncertainty are inseparable from these considerations. Cosmic radiation, micrometeoroid impacts, system failures, and unforeseen environmental hazards all accumulate over extended durations. Redundancy, adaptability, and autonomous repair systems become critical. Humans, or their artificial surrogates, must be prepared for contingencies that unfold slowly, yet carry profound consequences. Every decision, from energy allocation to habitat design, must account for both immediate needs and long-term sustainability, reflecting a balance between foresight and practical necessity. Dreams of the far future are therefore inseparable from the principles of risk management, resilience, and adaptation. Even sensory experience and perception are altered when thinking on these scales. Vast distances, altered light, and the absence of familiar environmental cues require humans to recalibrate expectations of space, movement, and orientation. The mind itself becomes part of the system, adapting to new rhythms, temporal scales, and spatial perspectives. Dreams of interstellar presence are thus intertwined with human cognition, inviting reflection on how perception, imagination, and experience may evolve as humans extend into the cosmos. Technological innovation continues to define the limits and possibilities of these dreams. Advances in automation, artificial intelligence, materials science, and energy storage all expand the envelope of feasible travel. Even small improvements in efficiency, reliability, or predictive modelling have profound cumulative effects when considered across decades or centuries. The far future, in this sense, is a horizon shaped by both imagination and incremental progress, where small insights accumulate into transformative capabilities over time. Ethical and philosophical considerations also emerge. Decisions made today regarding propulsion, life support, societal structures, and resource allocation have consequences that may extend centuries into the future. Human presence on a multi-generational ship or interstellar mission must reconcile the needs, rights, and experiences of individuals with collective goals and mission success. Responsibility, foresight, and a sense of stewardship become intertwined with technical planning, illustrating that dreams of the far future are inseparable from human values and the capacity for ethical reflection. Exploration itself becomes both literal and conceptual. Physical journeys to distant stars and the development of technologies to sustain life far from Earth are mirrored by intellectual journeys, understanding the universe, predicting cosmic hazards, and imagining societies capable of thriving in extreme environments. Human curiosity and ambition operate across both dimensions, shaping not only the design of spacecraft and life support, but also the framework of thought within which these endeavours occur. Dreams of the far future are therefore simultaneously practical and philosophical, guiding both engineering and imagination. Even the smallest innovations have cumulative significance. Improvements in resource recycling, propulsion efficiency, radiation shielding, or autonomous repair systems may seem incremental. Yet when extended over centuries, they create the difference between survival and failure, progress and stagnation. Long-term thinking is essential as each element interacts with others, forming a web of dependencies and opportunities. Dreams of the far future are built not on singular breakthroughs alone, but on a continuous, layered accumulation of knowledge, skill, and understanding. Ultimately, contemplating the far future of human space travel brings together every element previously considered: energy, matter, time, life support, social structures, technology, and ethics. These dreams are grounded in physical reality while inspired by imagination, challenging humans to extend presence, understanding, and culture across unprecedented distances and durations. They reveal both the limits of our current capabilities and the potential for extraordinary adaptation, demonstrating that human ambition is bounded not by imagination alone, but by the careful integration of knowledge, foresight, and resource management. Exploring the far future encourages reflection on human persistence, ingenuity, and resilience. Even in environments that are hostile, vast, and indifferent, life can endure through careful planning, adaptation, and innovation. Every element, from propulsion to resource management to social organization, contributes to the continuity of presence and purpose. These dreams are simultaneously technical, philosophical, and cultural, forming a coherent vision of what humanity might accomplish when ambition is tempered by understanding and guided by foresight. In considering these distant horizons, humans confront the profound scale of the universe, the limitations imposed by physics, and the resilience required to endure over time. The far future challenges our conception of life, society, and exploration, requiring both humility and audacity. Dreams of interstellar presence are therefore exercises in imagination and strategy, in which practical engineering, human psychology, and philosophical reflection merge. They illuminate what is possible when humans combine curiosity, creativity, and careful attention to the laws of nature. Even as we imagine the farthest reaches of human exploration, there comes a moment to pause and reflect on what it truly means to confront the infinite. The universe stretches in every direction, vast, silent, and indifferent, yet it also offers a stage for curiosity, courage, and ingenuity. Human space travel, from the first tentative steps beyond the atmosphere to dreams of journeys spanning decades, centuries, or even millennia, exists within this context. The pause in the infinite is not a cessation of movement, but a moment of contemplation, a space in which the mind can consider both the immensity of the cosmos and the fragility and resilience of human endeavour. Silence, in the vastness of space, takes on a tangible quality. Without atmosphere, sound does not travel. Without nearby points of reference, motion is relative and perception is challenged. In these conditions, every decision, every calculation, every breath taken by humans or machinery carries amplified significance. Pause becomes necessary, a chance to recalibrate, to appreciate the subtle interplay of energy, matter, and time that makes survival and progress possible. Even the smallest acts, adjusting a trajectory, monitoring a life support system, or reflecting on the stars outside a viewport, take on profound weight. They are the quiet markers of presence within an environment that is otherwise vast and unyielding. Distance, too, acquires new meaning in this reflection. Beyond the solar system, even the nearest stars are separated by expanses that defy comprehension. Light years, astronomical units, and parsecs are more than measurements. They are reminders of scale, of the patience required to traverse the cosmos, and of the careful orchestration of every element that sustains life in such remote regions. The ultimate limit of human travel is therefore a combination of distance, time, and the practicalities of biology and engineering, yet in pausing to reflect, we acknowledge that these limitations also frame the possibilities. They define the arena in which human ambition and ingenuity operate, providing boundaries that give structure to exploration rather than constraining imagination. Time especially becomes a central companion in this reflection. The relativistic effects that shape journeys at near-light speed, the durations required for generational or suspended travel, and the accumulation of centuries in transit all remind us that human perception is intertwined with cosmic scale. Travellers may experience months or years while decades or millennia pass elsewhere. This divergence between subjective experience and universal reality is both a practical consideration and a philosophical insight, inviting contemplation on the nature of existence, continuity, and legacy in environments that unfold on scales beyond ordinary human comprehension. A pause in the infinite allows the mind to dwell on these subtleties, recognizing the profound interplay between time, movement, and experience. Energy and matter, too, enter this reflection. Every gram of fuel, every watt of power, every ounce of consumable matter is meticulously accounted for, balancing the immediate needs of survival against the overarching goals of interstellar travel. Efficiency, redundancy, and foresight are not abstract virtues. They are survival tools, critical for maintaining both life and momentum in environments that provide no external support. The pause is a chance to appreciate how these elements are interconnected. Energy propels motion, matter sustains life, and both are constrained by physics and biology. Each calculation, each decision, becomes part of a continuum that spans the mission, and, in a broader sense, the ambition of human presence in the cosmos. The environment itself, vast and indifferent, shapes the quality of this reflection. Cosmic radiation, microgravity, extreme temperatures, and the silent void all emphasize that human existence is contingent upon careful adaptation. Habitats, life support systems, propulsion, and shielding represent the culmination of ingenuity applied to an environment that is fundamentally hostile. Even in moments of pause, the presence of these systems reminds observers that survival is not given, but earned through meticulous design, planning, and constant vigilance. The pause in the infinite is therefore a recognition of both fragility and resilience, highlighting how every measure taken in preparation enables continued existence against overwhelming odds. Psychological dimensions are equally profound. Isolation, confinement, and the absence of familiar terrestrial references amplify the significance of reflection. Humans must navigate both physical and mental landscapes, balancing operational responsibilities with the maintenance of awareness, morale, and cognitive health. The pause allows for an acknowledgement of these challenges, a quiet appraisal of the delicate interplay between mind and environment. Thoughts wander naturally to home, to Earth, to the generations behind and ahead, and yet there is a sense of continuity that extends outward, tethered not only to past achievements, but to potential futures. reflection becomes both a mental exercise and a method of sustaining equilibrium in conditions that are extraordinary in every respect. Even social structures take on a contemplative quality during these pauses. Generational ships, multi-decade missions, and suspended animation all require careful attention to social dynamics, education, and continuity. Every decision made about governance, knowledge transfer, or cultural continuity carries significance across decades or centuries. Pausing in the infinite allows for assessment of these structures, an evaluation of whether cohesion is maintained, whether knowledge persists, and whether the vessel, both as habitat and as society, remains functional. Human presence is not simply a matter of individual survival, but of maintaining a coherent, resilient community over time and distance. Speculative possibilities also shape reflection. Wormholes, warp drives, and theoretical propulsion systems expand the mind to consider what might one day be possible. Even if these remain beyond practical implementation, they provide a framework for understanding the universe and humanity's place within it. Imagining the manipulation of space-time, the bypassing of light speed limits, or the navigation of wormhole networks allows humans to situate themselves not only within known reality, but within the broader realm of potentiality. The pause in the infinite is, in this sense, both literal and imaginative, a moment to consider the boundary between what is and what might be. Ethics, philosophy, and purpose naturally emerge in this space. Decisions made across extended missions have consequences that reverberate for generations or even for the species as a whole. Resource allocation, risk management, and societal design are all suffused with moral and philosophical significance. Pausing allows for reflection on these dimensions, encouraging consideration of responsibility, foresight, and the integration of human values with technological and operational imperatives. The infinite surrounding these missions magnifies the weight of such reflection, emphasizing that survival is intertwined with thought, judgment, and intention. Even small-scale observations become profound during these moments. The movement of a distant star, the glimmer of a planet far away, or the subtle shift of light over time provides context for human ambition. The cosmos is silent, yet it communicates through scale, motion, and energy. Recognizing these patterns fosters both humility and wonder, reinforcing the sense that human exploration, no matter how advanced, is a dialogue with forces far beyond immediate control. A pause in the infinite offers an opportunity to witness these patterns, to integrate observation with reflection, and to situate human endeavour within the vast continuity of cosmic processes. Practical considerations are also illuminated. Energy budgets, material constraints, propulsion efficiency, and life support stability all become clearer when taken in a reflective moment. Assessing performance, anticipating failures, and recalibrating expectations are essential components of long-duration travel. The pause in the infinite is not mere leisure, it is an essential strategy for sustained operation, allowing both human and machine to integrate data, assess conditions, and maintain readiness for the challenges ahead. Observation, reflection, and assessment are intertwined with action, forming a continuous cycle that sustains presence in the void. Even imagination is sharpened during these periods. Considering the ultimate limits of speed, distance, and survival inspires creative solutions and new avenues of inquiry. Concepts that once seemed impossible, fusion propulsion, interstellar life support, or autonomous long-term habitats, gain context and meaning when assessed against the realities of current knowledge and the scale of the cosmos. Pausing allows humans to reconcile aspiration with reality, to balance hope with feasibility, and to generate strategies that extend presence while respecting the immutable rules of physics. Ultimately, a pause in the infinite is both a literal and symbolic act. It recognizes the immensity of the universe, the limits of human capability, and the remarkable adaptability of life. It provides space to reflect on survival, ambition, and the extraordinary engineering and social systems that enable human presence beyond Earth. It is a quiet acknowledgement of both fragility and resilience, a moment to appreciate the delicate balance that makes exploration possible. Within this pause, thought, imagination, and reflection converge, offering insight not only into the cosmos, but into what it means to exist, act, and persist as humans among the stars. Even as the pause ends and motion resumes, the reflection lingers. Decisions, observations, and insights gained during quiet contemplation shape subsequent action, guiding navigation, resource management, and human activity. Each movement forward is informed by the understanding accrued during these moments, ensuring that every step, every calculation, and every choice is anchored in awareness. The pause in the infinite is therefore an active moment, one that influences not only perception, but operational reality, merging thought with action in the ongoing journey through the cosmos. Space, silent and vast, remains indifferent, yet it also provides context, structure, and meaning. Human presence within it is defined by awareness, ingenuity, and reflection. A pause in the infinite is not surrender, but a deliberate engagement with scale, time, and possibility. It honors the fragility of life, while celebrating the resilience and creativity that enable humans to exist in environments that are otherwise inhospitable. Through this contemplation, the universe is both observed and understood, not in totality, but in a meaningful, deliberate way that guides continued exploration. Every final reflection returns attention to the balance between ambition and limitation. Energy, matter, time, and human endurance all converge to define what is possible. Even the quietest moment offers insight into the constraints and opportunities inherent in deep space travel. Pausing allows for assessment, calibration, and philosophical engagement, ensuring that each decision, each maneuver, and each aspiration is informed by an integrated understanding of the environment, the technology, and the humans who inhabit it. The pause in the infinite is therefore both restorative and instructive, guiding action while fostering appreciation for the vastness, beauty, and challenge of space.